Hi everyone, today we will learn about data preprocessing step, and this is a very important step in our machine learning models, and without this step our machine learning model will not work properly and efficiently. So let's get started with data preprocessing. In this, the first step is importing libraries. So in data preprocessing we need NumPy and Pandas for our preprocessing techniques, so we imported these two libraries. Now the second step is importing our dataset. Now for importing our dataset we will require NumPy module. So as the first line says, dataset equal to pd.readcsv, and in this we had passed our name of dataset, that is data.csv. Now pd.readcsv is the predefined method in Pandas for importing our dataset, and data.csv is our name of dataset. And in machine learning we will always use data sets which are separated by some delimiters, and in this data set the delimiter is comma. That is why we use our data as data.csv. Now before going further, let me see you our data set. This is our data set in which we have 4 columns and 10 rows. In this, the first 3 columns will consist of our features of matrix X, and the last column is our dependent variable Y. So now let's go to the code again. Now X equal to dataset.iloc. Here iloc is predefined method to import our desired columns. So in this square bracket we first write colon. The first colon represent all the rows in our dataset, comma colon -1 represent all the columns in our data set except the last one, dot values. Similarly for dependent variable Y equal to dataset.iloc, and in the square bracket we will first write colon, which means all the rows, comma 3, which means the third column, dot values. So let me first run this code so that you can see. Now as you can see, the X, Y and our data set, this is our data set which we had imported, and the X and Y. So let me see what is in X. This is our X, the first 3 columns, country, age and salary, and this is our Y, the last column. Now the third step is handling missing data. Now as you can see that in our X features of matrix, in the second column we had a NaN value which is not a number, and in third column it also consists of NaN which is not a number. And to handle this missing data situation we will use sklearn library to compute the missing values by replacing it with its mean. So let's see the code. So for this we will require sklearn library. So from sklearn.preprocessing import imputer. Now imputer is the class which we will use. Now the imputer variable is the object of class imputer. So imputer equal to class imputer, and in this class we will pass 2 arguments, missing values and strategy. The missing value is NaN and the strategy we are using is mean. After this we will calculate these missing values by using imputer.fit method and apply this method only to those columns which has missing values, not whole feature of matrix. So that's why we use colon comma 1 colon 3, which the first column represent all the rows, and 1 colon 3 represents the first and second column. So and after calculating we have to now apply this calculation in our feature of matrix X. So for this we use X colon 1 colon 3 equal to imputer.transform X colon 1 colon 3, so that our calculated results will transform to our feature of matrix. So first let me run this code. Now let me show you what I did done. Now as you can see, the place where it was previously written NA, and now there is a mean value of all the values in this column, and in this second column also you can see that the NaN is converted to the mean. So this is our handling missing data. Now the next step is encoding categorical data. Now as you can see, the first column in feature of matrix X consists of strings, and all the machine learning models will work only on numerical data, so we have to convert this string into numerical data. So for this we will use label encoder and one hot encoder. Now first we will see label encoder. So for this we will again use sklearn.preprocessing module. So from sklearn.preprocessing import label encoder comma one hot encoder. These two are the classes. Now for label encoder class we will make the object label encoder underscore x equal to label encoder. Now x square bracket colon comma 0 equal to label encoder underscore x dot fit underscore transform x square bracket colon comma 0, which means that we have to encode our all the rows of first column in feature of matrix X. So let me run this code so that you can understand what it had done. Now let me print the X again. As you can see, now the values Germany, Spain and France has converted to 0, 1, 2. Now after this, now in machine learning, one problem about label encoding is that it will assign numerical values to strings associated to them, and as you can see that 2 is greater than 1 and 1 is greater than 0, so the model will consider that 2 has higher priority than 1 and 1 has higher priority than 0, and it will make a relationship between Germany, France and Spain, and we all know that there is no relationship between these country names. So to avoid this problem we will use one hot encoder, which will do make 3 separate columns of each category, and this technique is known as dummy method. So let's see what one hot encoder will do. First we will make object of one hot encoder class. So one hot encoder equal to one hot encoder class. In this the only one argument we will use is categorical features, which is equal to square bracket 0, which means that we have to specify for which column we want to apply one hot encoder. So for in X we want the features categorical one hot encoding in first column, so we will write categorical features equals to 0. Now X equal to one hot encoder dot fit underscore transform X to array. Now after calculating the one hot encoder we now have to transform it to X, so the X equal to one hot dot fit underscore transform method will do this. So let's run this code. Now let me print X again. It's not making clear, so let's see from here. Now as you can see, there are 3 separate columns for 0, 1 and 2 for means France, Germany and Spain, and the rest of the 2 columns are previous. Now for Y also we have to label encode, because Y consists of yes and no label, so we will convert yes and no to 1 and 0. So for this we will only use label encoder. Now you can see that Y is converted to 0 and 1. Now the next step is splitting our data set into training and testing data, because in machine learning models we have to separate our whole data set into 2 parts, which is one part is for training, which will we apply for training our model, and one other half is of testing data, which will be used to test our model, so that we can understand how our model is progressing or learning. So for this also we will use sklearn, and in this we will use sklearn.model selection module, and from this we will import train, test and split class. Now for splitting our data, we will first create 4 variables that are x underscore train, x underscore test, y underscore train and y underscore test, which will equal to train, test, split, and in this we will pass arguments: the feature of matrix x, the dependent vector y, test size equal to 0.2, which means 20%, which means that our data set has to be separated. For training it will be separated 80%, and for testing it will be separated 20%. And the random state equals to 0. Its value can be any integer value. It's something similar to the seed value which we use in NumPy, and it's used for random selection of our samples in train and test variables. So let me run this code and see what it happens. So now as you can see, the variables are made. X train, it will have 8 values, 80%, and X test 2 values, 20%, similarly. Y train, 8 observations, Y test 2 observations. Now the last step is feature scaling. Now as you can see that our data set has 2 columns which has ranges differ. In each column the range is different, and in salary column the range is different, so it will make difficult for our machine learning model to understand the pattern, and the column which has highest range will dominate the column with lowest range. And to avoid this problem we will use feature scaling. And in feature scaling we have 2 techniques: standardization and normalization, and in this code we are using standardization technique. So for this we will again use sklearn.preprocessing module, and from this we will import standard scaler class. Now we will make an object of standard scaler class, that is sc underscore x equal to standard scaler. Now x train is equal to sc underscore x dot fit underscore transform x train, and similarly for x test equal to xc dot transform x test. Now let's see what happens. Now as you can see, the x train, all the now values are in similar ranges in columns. So this is had done with the help of standardization and feature scaling steps. So this is the end of data preprocessing. Thank you so much.
Hi everyone. Today we are going to learn about k nearest neighbor or KNN algorithm. So let's start with what is KNN. So KNN is one of the basic classification algorithm used in machine learning, and its main focus area is pattern recognition, data mining and many more. So let's see as how this KNN algorithm work. So this is an example plot in which there are 2 categories, category 1 and category 2. Now before applying KNN, we are taking a new data point somewhere in between of these 2 categories. Now after the KNN algorithm applies in this example plot, we get that the new data point is belong to category 1. So let's see how this decision is taken place. So let's see the step-by-step explanation of KNN algorithm. So the first step is to choose the number k of neighbors, which means we have to choose the k neighbors of these new data points, and the default value for this is 5. You can choose any value you like, but the default value which is used is 5. So now we are going to step 2. Now we have to choose these 5 points with the help of Euclidean distance. So the points which are 5 points closer to this new data points with the Euclidean distance are its 5 neighbors. Now in this step 3, among these k neighbors, count the numbers of data point in each category. Now these are the 5 neighbors which are nearest to this new data points, and now we will count the neighbors in each category. The category which has the more neighbors, the new data point will belong to that category. So category 1 has 3 neighbors and category 2 has 2 neighbors. So it's obviously that the new data point will belongs to category 1. So this is our step 4 and the KNN model is ready. So this is the basic concepts of KNN algorithm. Now we will see this in practical use. So let's see its implementation part. So here is the implementation part. As always, our first step is importing the libraries. The second step is importing the data sets. So let me run this code and import our data set first. So as you can see, this is our data set, consists of 5 columns: user ID, gender, ages, estimate salary and purchased. And from this data set we are going to use 3 columns: age and estimated salary as our feature of matrix X, and purchased is our independent variable Y. So this is a feature of matrix X, consists of age and salary, and the independent variable Y consists who is purchased the product or not. So now after this we are going to split our data set into train and test sets. So let me run this code and split our data set. So as you can see, our data set is splitted into X train, X test, Y test and Y train. Now after that we are going to apply feature scaling, because in classification the libraries we are using for our model to train does not implicitly apply this feature scaling, so we have to apply it explicitly. That's why we are applying the feature scaling on our X train and X test. So the feature scaling is applied. Now you can see they are in the same range, salary and age. Now after that, the main step, which is the generation of our model, and for this we are using as always sklearn library, and from sklearn we are using .neighbors module, and from this module we are importing kneighbors classifier class. Now the class is imported. Now we have to initialize our object. So classifier is the name of object, which is equal to the name of class, and here are the parameters which we are going to use. So let me show you which all are the parameters this class is having. Now the first parameter is n neighbors, which is the number of neighbors you want for a new data point. So as always we are using the default value 5. Now the second parameter matrix, which is a default parameter. If you don't mention it, its value is Minkowski, and this metric equal to Minkowski is used for Euclidean distance, and the p is also a default parameter and its value is also equal to 2, the default value, and it's also used for Euclidean distance. So this you have to remember. Now after initializing our object, now we have to fit our model. So classifier.fit x train comma Y train. So let me run this code. So our model is trained now. Now after that we are going to predict our X test results. So now let's see, this is our Y test and this is our Y pred. So as you can see, the first all of from 1 to 7 the predictions are correct. There is one incorrect prediction in 9. So and to see what are the total incorrect predictions, we are going to use confusion matrix. So let's run this code of confusion matrix and see our confusion matrix. So in this matrix, the diagonal opposite to the principal diagonal, that is 4 plus 3, which is equal to 7, are our incorrect prediction in this total model, the prediction of models. So this is the practical approach of KNN. So thanks for listening this video.
Hello friends, welcome to the course on machine learning. Today we are going to start with a new concept, that is SVM. Now in regression there was a concept like SVR, support vector regression. This topic is quite similar to it. It is SVM, that refers for support vector machine. Now SVR was for regression and support vector machine is for classification. So first we are going to start by getting an understanding of intuition behind the working of SVM, and then we are going to implement it in our code. So let's get started. First of all, let's say we have some data points, as you can see here, these red data points, and there are green data points. Now we want to make a classification model which is going to classify these data points as red and these data points and green. So our model is going to create a line which is going to separate them as well effectively. The best fitting line can be like a horizontal line, it can be a vertical line as you can see here, and it can also be a diagonal line. Now there can not only can be one diagonal line, it can be anything like 3 diagonal lines like this and like that. Let's say there are 3 models, and all the 3 models split both the red data points and green data points now. But these this best fitting line doesn't affect the data point for training but for the testing. This line is important for the classification because it is going to classify the data point. Suppose let's say we have a data point around like here, so for the first line it is going to classify it as a red data point, but the second line, that is the middle one, which is going to classify that red data point as a green. Now it is required to have an optimal line which is going to split and classify all the data points effectively. So in order to do that, we are going to use the margin concept that is similar to the SVR. So to do that, it is going to fit the model with a line with the maximum margin between the data points, and these data points will be equidistant from each other. Now the data point that is going to choose will have a specific property for like it is going to pick a data point from the red data set which have the most traits common with the green data points compared to the others. So for this red data point will have more traits compared similar to the green data points compared to these, and similarly for green data set this data point will have more traits similar to red data points compared to this data compared to the remaining data points. So it's going to pick those data points and going to create a line to fit this in such a way that they will be equidistant from each other and will have the maximum margin between them. And in this manner they are going to create a model line, then they are going to create a line which is going to split and classify both the data points. And that's why these data points will be referred as support vectors. Now the margin and equidistance and the best fitting line will only depend on these support vectors. Even after, if you have only these 2 data points and suppose like these data points are not available and these data points are also not available, there are only these 2 data points are available, so the model is not going to change because it depends on only these data points. Now why these data points are referred as support vectors? Because it's just a two dimensional. Suppose there are many variables like 3, 4, 5, 6, 7. So in 3D space these data points are referred as vectors, and they work similar to as vectors. So that's why they are referred as support vectors, because they are supporting our classifier here. As you can see here, these data points will be treated as a support vectors. Let's say we'll start with an example. Suppose we want to make a classifier that is going to classify oranges and apples. So let's say there are data points like there and here which are of the apples and normal oranges and like that, but support vector machine doesn't work on them to classify the object, else it works on the exception. As you remember, I said before that it depends on the data point with the traits most similar to the another class, that so it will be like it's going to classify on the basis of the apple. As you can see here, this apple looks similar to the oranges, and similarly it will treat it will also take an orange that looks similar to the apple and things like that. As you can see here, is this green orange? Oranges are usually orange, they are not green, and it's less bumpy compared to that, and it looks similar to the green apple. So it's going to take exceptional data and then it's going to fit line on the basis of those by taking them as a support vector and creating a line, or I mean splitting on the basis or using a line with the equidistance from those data set and with the maximum margin between them. So that was the basic intuition behind the working of SVM. So let's try to implement it in our code. As you can see here, let's start by importing our required libraries, which is NumPy and Pandas. After importing libraries, let's say we have a dataset social network ads.csv. So let's say using the same dataset, let's create a data frame named dataset using pandas library dot read csv function, and then we pass the csv file, I mean our dataset. After that, we used dataset iloc method and created our independent variable and dependent variable x and y, and in which we pass colon for all rows and 2,3 for age and salary, and similar to that we use colon for all rows for dependent variable and 4 for our output, which is purchased or not purchased. We use dot values to convert it into array. So after executing this line of code, as you can see here, that's the dataset that we are using: user ID, gender, age, salary and purchase. And we created two variables, our independent variable x, age and salary, and our dependent variable y. Now after that, first we are going to split our dataset into training set and testing set. So let's say from sklearner.model selection we import our function train test split, and then we are going to use it to split our both the independent variable and dependent variable into training set and testing set. So we are going to pass xtrain xtest ytrain ytest equals to our function train underscore test underscore split, and then there we pass x comma y, our independent variable and dependent variable, and then we specify text size, which is 0.25, that is 25% for testing and 75% for training, and then we specified random state equals to 0. Now after that, we need, as you remember, we need to apply feature scaling on it, because age and salary are not quite comparable. So we are going to use it like from sklearner.preprocessing. We are going to import standard scalar class, and then we are going to create a class an object of standard scalar class, that is sc is equal to standard scalar. After that, we are going to apply feature scaling on both xtrain and yxtest. So let's say xtrain is equals to sc dot fit underscore transform, which is going to fit the feature scaling first, and then it's going to transform the training set. So we are going to use sc dot fit underscore transform function, and in which we are going to pass xtrain. After that, we are going to apply feature scaling on testing set. So xtest is equals to sc dot transform x underscore test. We only used transform because we already fitted our feature scaling on data. We are going to transform it into using feature scaling. Let's execute the above the line of code. As you can see here, we got xtrain xtest ytrain ytest. Now after that, you can also see that we apply feature scaling on xtrain and xtest. Now we are going to import support vector classifier, that is our classifier class, models class, already available in sklearner.svm. So we are going to import it using from sklearner.svm import svc. Now after executing that line of code, we are going to create an object of svc. Let's say we create a model named classifier equals to svc, and then we are going to pass kernel is equal to linear and random state equals to 0. Random state is equal to 0 for not using the random data points for more training, and not picking random else. Now here kernel is equal to linear. There are many types of kernel already available for training. As we are going to use linear here, we are going to get an understanding of the kernel or why it's required in the next session in the kernel SVM. So let's put it linear as it is, and then we are going to put random state equals to 0 here. So we don't want any random equips of data points for our training. So after executing this line of code, it's going to create a model named classifier, as you can see here. After that, we are going to fit, or I mean train it on the basis of training data. So we are going to use classify.fit, and then we are going to pass xtrain and ytrain here. Let's try to make prediction using our classifier. So we are going to use ypred equals to classifier dot predict, and in which we are going to pass x underscore test, that is our training set data. After that, as you can see here, that's the prediction that our model made, and x and y test is the prediction actual value. The y test is the actual value, so you can compare these values. They are totally similar. As you can see, our model make prediction 0 0 0 0 0 0. They're also 0 here, and it's 1 on the 7, and 8 9 10 are 0. So it seems that it's making good predictions. So in order to get the accuracy, we are going to compute our confusion matrix. So for that, from sklearn.matrix, we are going to import confusion matrix first, and then we are going to create an object of confusion matrix, that is cm is equal to confusion matrix, and then we are going to pass both the values, the actual value and the prediction, so y test and y pred. Now after that, this is the cm, that the confusion matrix that we just created, and as you can see here, the above values are actual value, and the value on the left are the prediction made by our model. As you can see, the actual value was 0, and our model makes 0 also for around like value 66, and the actual value was 1, and our model made a prediction of 1 also for a value around like 24. So as you can see here, it makes quite great prediction, and adding the value 66 and 24, it gives 90 out of 100. So the model making prediction and the accuracy of 90%, and that's quite great. So that means our model making quite great predictions. So that's it for our today's session. In the next session, we are going to start by understanding the kernel, what is the use of kernel, why it required, and we are going to understand the concept of kernel SVM. Now that's it for our today's session. Hello friends, welcome to the course on machine learning. Today we are going to start with the concept that is about kernel SVM. In the previous section we have seen about SVM. Now today we are going to just try to understand what is kernel and why it is required in the SVM, and what is the use of it, and what is the intuition behind it, and how it works, and things like that. So let's get started. First of all, you may have seen this image before. I mean, in this we have some certain data points that are available, which is green and red, and then we try to use a SVM to create a line. Here in machine learning, that splitting line is referred as hyperplane. So the SVM model will try to create a hyperplane which will try and classify these data points, and which will be like this, a linear straight line between both the data points. Now certain cases comes when we can see data points like this. As you can see, the red data points are surrounding the green data points, and we can create a line. I mean, we can create a hyperplane, or model can create a hyperplane which will split the data points or to classify them. Now even if you try to create diagonal line, vertical line, horizontal line, I mean, you can split or classify the data points using a linear separator or a linear hyperplane. So how are we going to deal with such problems? So to deal with that, there are different type of kernel available to us. Now what is kernel? Just think of it, kernel, as different type of approaches to split or classify these data points, which can be anything, and they have their own different mathematical functions. We are not going to deal with the different mathematical functions. We are just trying to understand them. So as you can see, even if you create a line which split which classify all the green data points above, you can't classify the red data points. So the model accuracy will be low using a linear kernel. Why it is? Because the data points on the right hand side, they are not linearly separable, and they need to be linearly separable. So there are various kernels. What they do is they try to make it a linear separable using their different approaches. So let's say, as you can see, this is the example as same as before. Let's say we want to classify green apples and yellow lemons, and we are using our SVM model. So if you use a linear kernel, it's not going to make a good classification. So in order to do that, we are going to use non-linear kernels. There are various non-linear kernels available, and the best and default one is RBF, that is radial Gaussian function. And other than that, there are other kernels available such as polynomial, linear, and etc. Now how they do is they try to add another dimension using their specific function which will split these data points, and think of it like that, and think of this axis, or think of this 2D visualization as you are viewing it from a top view, and when you try to view it from a side view and use another axis which is here x2, then it will be like clear here that the green apples and yellow lemons will be different from each other on the specified function which is applied on x2. And then our model will try to create a hyperplane which will split them. To understand that, let's try to see a simple example. Let's say we have data points available here and we are viewing from side view. You can think of it as a top view will be the same as before. Now see, you can see the green apples are surrounding the yellow lemons. Let's say we added another dimensionality by adding another axis which is x2, and we will apply a function which is x square here. We all know that the x square function create a curved line from 0 on both right hand side and left hand side. Just think of it that applying this function over this axis and then projecting the data points over the axis, you can see that the green apples will be on the curve and yellow lemons will also be on the curve, and you can create a hyperplane which will split these data points from each other and will make a classification model. You can see that the green apples and yellow lemons are now separate. They are not linearly separable, they are now separate because of adding a new function by adding another dimensionality into it, which means we are making this 2D dimension space into a 3D dimension space by adding another dimension. Now there are different types of kernel available, such as linear, poly, RBF. As you can see, this is the linear kernel that we use. It is the RBF kernel and it is polynomial kernel. There are different type of kernel available in our SVC class. You can see here linear, poly, RBF, sigmoid, pre-computed, and they all have their different approaches to split these data points to make a classification model accurate. And they all have their pros and cons. You can try to change the kernel in our code, and you can try to change and play around with the code of the previous section by changing its kernel and check its accuracy, that how accurate it's predicting. As you can see, this is the whole code that we understand in the previous section about the SVM. All we are going to do is we are going to change the value of kernel that is available here, which was linear first. We applied RBF here and it's by default RBF2. So let's try to execute this. You can see that it created a confusion matrix, and you may remember the accuracy was around like 90% from SVM using a linear kernel. You can see here it makes the classification with accuracy of around like 64 plus 29, that is 93. So it makes an accuracy of around like 93%, which is 3% more than the previous. So it's quite great. You can try to play around with the code and by changing the kernel to different values such as sigmoid, poly, and Gaussian and others. Now that's it for today's session.
Hi everyone. In this session we are going to learn about decision tree classification, and this is going to be a very short session because I'm only going to explain the coding part and not the concepts of decision tree, since the concepts were discussed in the previous videos of decision tree regression. So I'm only going to explain you the coding section here. So let's start with the coding section. So the first step is importing libraries, the second is importing dataset, and the same datasets we are using for all our codes for practice. And the third step is we are splitting, as you all knows. Now the fourth step, which is a much important step if we are training a classification model. Now then we are going for the fifth step, which is our main step, our training model such step. So for this we are using sklearn module. So from sklearn.tree we are importing decision tree classifier as the class. Now after importing class, our object has to be initialized, so it's classifier equal to decision tree classification. Now in this we have to provide two parameters. The first is criterion, and this is used for the homogeneous splitting of the data. As you know, in the concept section I told you about how the decision tree algorithm works by splitting our data sets into different regions. So this criterion parameter is for this purpose. And now the second parameter is random state, which I already explained. So now after initializing our object, we have to now fit our model. So classify.fit xtrain comma ytrain. So let's run this whole section from this to the top. So our model is trained now. Now we have to predict our x test. So it's predicted. Now let's see what is y pred here and y test. So you can compare the correct and incorrect prediction years, and if you don't want to serve this and waste your time, then you can directly run the confusion matrix code and see what are the incorrect predictions. So as you can see, there are 6 plus 3 9 incorrect predictions. So our model is good than the previous models we learned. So this is all about decision tree classification. If you have any doubt, please discuss to us. Thank you. Hi everyone. In today's session we are going to learn about random forest classification, and I previously discussed the random forest regression concepts and theories. So the concepts are the same, but in this classification module we are going to use a different sklearn library for the classification, and the rest of the concepts are similar because the random forest is same. So let's start with the implementation part. So the first 3/4 steps are the same, that is importing our libraries, the importing our data sets, which is social network, which is we using from previous models only, and the third is splitting our data set. Then after then the feature scaling, and then our main important step, which is training our model. So for this we are using sklearn.ensemble module, and from this module we are using importing random forest classifier class. After importing our class, now we have to initialize our object for this class. So the object is as always classifier, and which is equal to random forest classifier class. And in this class we are going to pass three parameters. The number one is n estimators, which is the number of decision trees, and the value we are using here is 10, which is the default value. Now the criterion parameter, which is equal to entropy, is used for homogeneous splitting of data set, and the third one is random state, which is equal to 0. Now after passing the parameters and initializing our object, now we have to fit our model. So classify.fit xtrain comma ytrain. So let me run this code from here to the top and train our model. So here our model is training, as you can see in the console. So our model is trained now. After training our model, now we will predict the result. So this is ypred, which is the prediction of y test. This is y test. So you can see that for first 10 observations are same, only the one is incorrect. So if you want to identify the total incorrect prediction, then we can use the confusion matrix and see what are the incorrect predictions. So 5 plus 4, which are 9 incorrect predictions. So this is similar to the decision forest classification. So this is all about random forest classification. So here our classification algorithm finishes, and after that we are going to the new chapter, which is unsupervised learning, and see what will happen in there. So thank you for listening this session.
Hello friends, welcome to the course on machine learning, and today we are going to start with a simple approach of simple linear regression. Now there are basically two most important and popular approaches that are mostly used with machine learning, that is regression and classification. Now regression is all about predicting the value of dependent variable on the basis of independent variables, such as for example, let's say an Uber. Now in the Uber app, it predicts out the fare charge of our ride. Now it predict the value of fare on the basis of distance it's going to be travel, and how much time it's going to take, and also how much traffic available in the route, or something like that. Now similarly, classification is all about classifying objects. It can be like from images, as per like classifying the image, whether it's the image of a dog or a cat or a person. So let's start with the concept of simple linear regression. Now in order to understand it, let's try to get its intuition or how it works. Now to understand the concept of simple linear regression, we are going to see the equation of simple linear regression, which is like this: y is equal to b0 plus b1 into x1. Simple linear regression only works with only one independent variable and a dependent variable. Now here our only one independent variable, that is x1, and dependent variable is y. Now it's going to do is compute the value for y by computing the equation where b0 is the constant. B0 constant is the base value, or it's like the best fitting line of a model intercept on y-axis, I mean where it intercept on the y-axis. And second is b1, that is our coefficient. It defines how much the value of dependent variable y going to change as the value of independent variable x1 changes. It can be like treated as a slope of in the equation, and x1 is our independent variable. Let's just see a graph to get a clear understanding behind the simple linear regression. Let's see, this is our graph where x is our independent variable and y is our dependent variable. Now you can see this is the intercept of line of our model on y-axis, and it's the value of b0, which is like 10, and b1 is the slope of line. Now here let's see these, let's say these all the black points are the data points of our data set. So how the simple linear regression going to create this line, I mean the best fitting line of our data set? So it's going to be created by calculating the error term for the line. Now what is the error term or error rate E? Now let's say for the black point the value of a y is like 10, but for our model it predicted the value here, which is going to be like at 13 or something like that. So it's going to first calculate the difference between the actual value and the predicted value, and then it's going to square, so that it's not going to be like this error is positive and this error is negative. They are both going to be treated as same, and then it's going to sum up the error rate of all the values. So for the error rate, the equation will be like sum of y, which is actual value, minus y hat, which is the predicted value, and the whole square of it. Now similarly, it's going to compute the error rate for many lines in such a way that the line with the minimum error rate is going to be treated as the best fitting line for our data set. So this is all the intuition behind our simple linear regression. Now let's see it in our code. First, we are going to import all the required libraries, which is NumPy, Matplotlib, and Pandas. NumPy for data array manipulation, Matplotlib for data our model visualization, and Pandas for data manipulation. Now first, we are going to create a data frame named dataset using Pandas, that's pd.readcsv, where we are going to pass the dataset, that is our salary underscore data.csv. This is the dataset we are going to use. We have only around like 30 rows and 2 columns. 2 columns are about years of experience, salary, and we are going to create a model, a simple linear regression model, which is going to predict the salary on the basis of years of experience of the person. So let's see it in our code. First, we created 2 variables, x, which is our independent variable, and y, which is our dependent variable. Here we use dataframe.iloc method, and then we are going to specify the columns that we required for the data variable. Now in the square bracket, we specify first as a column which defines from start to end. That means it access or it returns all the rows from starting index to the ending index. And second, we pass colon -1. This defines from starting to the ending index, but exclusively to the ending index. That means -1 defines the ending index, but it's going to exclude it out from the range. So that means nor it access all the columns except the last column. And here in our data set there are only 2 columns, so it's going to access the first column only. So it's going to return the first column, which is years of experience. We can also use 0 here instead of column -1. That's going to specify the column at 0th index, that is our first column. Now after that we created an independent variable using dataset.ilog, where we defines all the rows, comma, the first column only, that is the salary, and use dot values to convert it into an array. So now let's execute this line of code. Now as you can see here, this is the data set and the data frame that we created, where in the first column is at index 0 is years of experience, and second column is salary. There the index starts from 0 to 29, that means we have 30 rows. Now then we created independent variable x, that is years of experience, and dependent variable y, that is salary. Now after that we need to divide or split the data of dependent and independent variable in training set and testing set. So this is carried out by an inbuilt function, that is train and underscore test underscore split. It split the data variables x or y into training batch and testing batch. And this function is already inbuilt and available in model selection package of sklearn. So we are going to import first this function into our code. Now after importing the function train underscore test underscore split, we are going to use this function to split the data variables into training set and testing set. So we are going to use the function. So we created 4 variables, then as you can see here, and these are the variables going to store the value returned by the function, and the function returns 4 values in the order like first independent variable of training set, independent data for testing set, dependent data for training set, and dependent data for testing set. And as you can see here, we use the 4 variables here, and then we pass the value returned by the function to them. So we use train underscore test underscore split function here and passed independent variable first and then dependent variable, and then we use test underscore size parameter and assigned value equals to 1/3. It defines that it's going to fetch 33% for the testing data and 66% for training data. And then we assigned random state equals to 0, so it's not going to pick random data rows from data variables. Now after that we are not required to perform pre-processing our data because the data is already pre-processed. So we are going to create our model. So let's execute this line of code first. Now after that, as you can see here, it creates xtrain, xtest, ytrain and ytest variables. Now xtrain and ytrain denotes the training data, and xtest and ytest denotes the testing data, where xtrain contains independent variable, that is our years of experience, and ytrain contains salary, that is our dependent variable of training set. Now our data is already pre-processed, so we are not required to pre-process our data first. So we are going to directly create our linear regression model. So first, there is already a linear regression class available in linear model package of sklearn. So we are going to import it first. After that, we created an object of linear regression class, that is regressor, which is going to be our model. As you can see here, it's a variable regressor which is going to be a linear model. Now after that, we are going to fit our regressor into training data. So we are going to use regressor.fit method, and then we are going to pass training data as independent variable of training data, which is years of experience, and a dependent variable of training data, that is salary, and it is x underscore train and y underscore train. So after fitting a regressor into the model, it's ready to make predictions. So as you can see here, it creates a linear regression model. Now after creating our linear regression model and fitting into a training set, it's ready to make prediction. So in order to validate, we are going to make predictions over test independent variable of testing data. and then we are going to compare it with dependent variable of testing data with the prediction we made. So as you can see here, we use regressor.predict function and make predictions of x underscore test, which is independent variable of testing data, and store the output of the prediction into y underscore pred variable. So executing this line of code will create a y underscore pred which contains the prediction made by our model. Now we are going to compare it with y underscore test, that is the actual value. Now as you can see here, our model is made the accuracy of around like 40,000 and the actual value salary is around like 37,000. So it's quite a good prediction. But for the second, as you can see here, our model make a prediction of like 1,23,000 and actual value is around like 1,22,000. So it's quite a great prediction also. But sometimes it's not make quite great prediction, such as here it make a prediction of around like 65,000 salary, but the actual value is around like 57,000 salary. So it's not quite great, and the main reason is we use less amount of data for fitting our regressor model. Now let's visualize our model. So for visualization, we are going to use matplotlib library. As you can see here, we imported pyplot of matplotlib library as plt, and then we are going to use it for visualization. Now as you can see here, we scattered first all the data point of training set, which is plt.scatter, and then we passed an independent variable of training set and dependent variable of training set and set the color equals to red. So it's going to scatter all the data points in red color in our graph. And then we are going to make a plot of testing side, but not with dependent variable of testing set, but with the prediction made by our model. So we are going to use plt.plot, and then we passed x underscore test, and then for prediction we use regressor.predict and also then passed x underscore test. So it's going to return y pred, I mean prediction made on the independent variable of testing set, and then we set the color equals to blue. Now after that we assign the title to the plot, which is salary versus experience, and then we assign label to the x-axis, which is our independent variable, that is years of experience, and label to the y-axis by plt.ylabel as salary, and then we are going to show our plot. So after executing the code, we are going to see visualization of our model. So let's execute this code. As you can see here, this is the visualization of our model. It's against years of experience and salary, where years of experience is our independent variable and salary is dependent variable. As you can see here, these red points are the scatter that we created here in this line of code. These are for the training set, and this blue line, that is plot that we created on testing set and its prediction. And this is our model. This is our simple linear regression model. So that's it for our today's session. Hello friends, welcome to the course on machine learning. In the previous session, we have seen about simple linear regression. So in this session, we are going to start with a new concept, that is multiple linear regression. First, we will try to get the understanding of the intuition behind the multiple linear regression, and then we will try to implement it in our code. So let's get started. Now first, what is multiple linear regression? Now you may know that in simple linear regression there is only one independent variable available and dependent variable depends on it. Now in multiple linear regression there are multiple independent variables available to us, and we are going to make a model that's going to predict the value of dependent variable on the basis of independent variables. Now they can be more than one, like 2, 3, 4, 5, or can anything. Now you may have seen this simple equation of simple linear regression. Today we are going to talk about multiple linear regression, and it's the equation of it. As you can see, it's the independent variable y, which is equals to the constant b0 and the coefficient b1, b2 to bn corresponding to the independent variable x1, x2 up to xn. Now the working is all similar, it's just that there are multiple independent variables available. Now b0 is the same constants, that means the intercept of line over the y-axis, and b1, b2 and bn are coefficients related to the corresponding independent variables. Now, so this is all the basic intuition behind our multiple linear regression. So let's try to implement this in our code. So we are going to start by importing our libraries first. Now as you can see, we imported numpy as np, matplotlib.pyplot as plt, and pandas as pd. Now after that, we are going to import our dataset. As you can see in this line of code, we created a data frame named dataset using a function of pandas.readcsv, by which we are reading a CSV file which is going to be our dataset, that is 50_startups.csv. Now this is the dataset that we are going to use. Now we are going to create a multiple linear regression model from this dataset that is going to predict the profit of the startup on the basis of its R&D spend, its administration, marketing spend, and the state where it's located. Now, so as you can see, profit will be our dependent variable y, and all the other 4 columns, that is state and the spends, R&D spend, and like, they are going to be our independent variables. Now let's first import a dataset into the code. After that, we are going to create our independent variable x, that is equals to dataset.ilog method, where we use colon first, which is going to return all the rows of our dataset. So here colon -1 is going to return all the columns except the last one. And similarly, we are going to create our dependent variable y from our dataset using .ilog method. So we are in dataset.ilog, and in square bracket we used column comma for all the rows from starting to end, and 4, that means the column at the 4th index. So after executing these 2 lines of code, we can see that we got 2 variables x and y, where x is our dependent variables, which is R&D spend, marketing spend, state, and etc., and y is our dependent variable, that is the profit by the startup. Now first, as you can see here, in our independent variable x, there is also a categorical data, that is state, which is New York, California, Florida, and these values are repeated. Now we can't just fit our model on the basis of the values of state. We need to convert it into its numeric representation. So first we are going to use label encoder on these values, and then we are going to use one hot encoder. Now what is label encoder and what is one hot encoder? So first let's try to understand this. So label encoder is going to convert the categorical values into its numeric representation. What it's going to do is first assign a numeric value to each categorical values, such as here as you can see there are 3 categorical values: caliber, ovary, uvo. Now it's going to assign a numeric value to all of these, such as 0, 1, 2, and then it's going to replace the value in the data set by its numeric representation, such as here it's caliber, so it's going to replace it with 0, and here it's uvo, and the value uvo it's assigned is 2, so it's going to replace it with 2, and similarly with ovary it's going to replace it with 1. Now we still can't use these values to fit it into our model. Now why is that? Because our model totally works on the numeric values, and it's going to work on the basis of numeric relation. So our model can possibly think of it as that the value 0 is comparatively lower compared to the value 2, which is comparatively higher value compared to the value 1. So we don't want such a comparison between these values, because they are not comparatively related to each other. So that's why we are going to apply one hot encoding on it. Now what's one hot encoder do? Now suppose let's say this is our data set, and there are few categories, such as categorical values such as Volkswagen, Acura, Honda, and like that, and their level encoding values will be like for Volkswagen 0, Acura 1, and Honda 2. So one hot encoding is going to create few new columns which will be equals to the classes available for our categories, such as there are 3 classes such as Volkswagen, Acura, and Honda. So it's going to create 3 new columns such as Volkswagen, Acura, and Honda, like that, and then it's going to assign 1 for those values where there is Volkswagen and 0 for the remaining one. So let's see here it's a Volkswagen, so it's going to assign 1 here and 0 for all the values. Here for in the Acura column, it's going to assign value 1 for the Acura, and for the remaining value it's going to assign 0. Similarly for Honda, it's going to assign 1 here and 0 here. So we need to implement this into our code to use the column state for our model prediction. So let's see it in our code. So first it's going to apply label. First we are going to apply label encoder on this. So it's going to assign numeric values to these states such as New York, California, Florida, and then it's going to convert them into one hot encoder. And so let's try to implement this into our code. So first, for label, there are already available classes of label encoder and one hot encoder in our sklearn.preprocessing package. So we are going to import them first. Now after importing, so we are going to create an object of label encoder class. So as you can see here, we created an object named label encoder underscore x of a label encoder class. We need to apply label encoder on the third column, which is of state. So we are going to use label encoder object and are going to use its function fit underscore transform. Now fit underscore transform is going to first fit those values into a label encoder object and then going to transform them into its label encoding, such as 0, 1, 2 and like that. So we need to apply it on the third column. So we are going to pass only the third column. So we use independent variable x, and then in the square bracket we assigned column for all the rows and comma 3 for only the column at the third index. And then we are going to store this at the third index column. So we are going to use x square bracket column for all the rows comma third column, means the column at index 3. Now after executing these two lines of code, it's going to encode them in its numeric representation. So let's see. As you can see, all the state values are encoded into its numeric representation. As you can see, it was California and New York and Florida here, and now it's 2, 0, 1. It may have assigned values 0, 1, 2 to the values such as Florida, New York, California and like that. Now after that, we are going to convert this numeric representation, I mean these label encoded values, into one hot encoder values. So first, for that we are going to create an object of one hot encoder, which is one hot encoder equal to one hot encoder square bracket. This is our object. So after creating the object one hot encoder, we are going to use the object and you are going to use its function fit underscore transform. Now using the fit underscore transform over only the third column, because we only required to apply one hot encoding over the third column specially. So we are going to use independent variable x, and in the square brackets we are going to pass colon for all the rows and square bracket 3 for the third column only. And then we are going to use dot to array to convert the output of the one hot encoding into an array format. And let's assign it into a new variable. Let's say it's a. Now after that, there is a problem occur sometimes, which is a dummy variable trap. So in order to understand that, let's try to see it into a image. This is the code related to our example. As you may have seen here, these are profit, R&D spend, admin, marketing, and this is the state. Now the equation related to this will be like B0, B1 into X1 for R&D spend, B2 and X2 will be admin, plus B3 into X3 will be marketing. Now for the state, we applied label encoder and then we applied one hot encoding in this variable. And as you can see, it converted this column state into New York and California and assigned the value 1 to the New York column and other as 0, and assigned 1 for California and California column and other as 0. Now after that, let's see these two columns. First, as you can see here, New York column is equals to 1 minus California. Now if we use both the variables, both these dummy variables into our program or into our model, so it's going to just duplicate the variable, as like both the variables are same. As you can see, if we only use this variable for our model, so it's going to say that 1 for New York and 0 for California. And similarly, if we use this, so it's going to state 0 for New York and 1 for California. We can use that. So using both the variables together is going to duplicate the variables into our model, which will increase complexity and reduce the accuracy. So this problem is referred as dummy variable trap. So it's not just for the binary, it's also that if there are multiple classes for one hot after one hot encoding, then we are going to use one less than the total number of classes. So if there are 3 classes, then we are going to use 2. If there are 5, then we are going to use 4. Similarly, we are going to use this concept in our code. Now, as in our code, we have a categorical variable that is state, and there are 3 classes, which is New York, California, and Florida. So we are going to avoid the dummy variable trap, we are going to drop one of the column of one hot encoder. So let's first execute this line of code to have a better understanding. As you can see, it created a new variable A. There are 3 classes 0, 1 and 2, and they are for New York, Florida and California. So to avoid dummy variable trap, we are going to drop one of the columns from it. So we are going to use this line of code. What this line of code is going to do is just assign an array to itself, passing the same array, and then in the square bracket we are going to use colon for that refers all the rows from start to end, and then one column which is going to return all the columns from first index to the end. So it's going to drop the column at index 0. So let's execute this line of code. So as you can see here, now we have only 2 columns. It dropped the first column that was before this, and then now it's only have 2 columns. So in this way we are going to avoid the dummy variable trap from in our model. Now we are going to use this 2 column and going to concat it into our independent variable x. So first we need to remove the state column from our independent variable x. So we are going to use the similar process. We are going to use x assigning the value to the itself, and then we are going to use x in square bracket. We are going to use colon for all the rows, and then colon 3 for all the columns x before the third column. So it's going to return the column at index 0, 1 and 2, but not the third one. So after executing this line of code, it removes the label encoding of state column. Now after that we are going to concat both the values at column wise, so at axis 1. So we are going to use numpy for concatenation. As you can see, we are going to assign the value at independent variable x, and then we are going to use np.concatenate, and then here in this parenthesis we are going to first pass both the variables, I mean both the arrays, that is capital X and a of the one hot encoding values, and comma assign x is equals to 1 so that it performs column wise. So let's execute this line of code. So as you can see here, now we have all the 3 values, which is R&D spend, marketing and administration, and then both only 2 columns for of one hot encoding format and not 3 to avoid the dummy variable trap. Now we are going to split them into our training data and testing data. So we are going to use the similar process as before. From sklearn.model selection we are going to import function train test split. So it's going to return 4 values as before. It's going to return independent variable of training data, independent values of testing data, dependent variables of training data, and dependent variable of testing data. And then we are going to use train test split, and here we pass both the independent variable and dependent variable, and then we pass test size, which is our 0.2, means 20% will be for test site and 80% will be for training. And then we assign random state equals to 0. Similarly, so no random shuffle or random values of rows are going to be picked up from our independent variable and train dependent variable. So after executing this line of code, we will be going to have 4 arrays for training data and testing data of their dependent and independent variables. So these are the xtrain and xtest, ytrain and ytest. Now first we are going to create our linear regression, multiple linear regression model, and then going to fit our training data into it, and then we are going to make prediction for the testing data. So it's same as before. We are going to import linear regression class from our linear model package of sklearn. So let's import it first. After that, we are going to create an object. Let's call it regressor and of linear regression class. As you can see, it's going to create an object regressor, which is a linear regression model. Now we are going to fit our model on training data. So we are going to use fit function. So regressor dot fit, and then we are going to pass xtrain and ytrain, and that are the independent and dependent variables of our training data. So after executing this line of code, now our model linear regression model is fitted. So we are going to use it for make prediction. So let's say we use regressor dot predict function and we are going to make prediction on x test, that is independent variable of testing data, and then we are going to store the value at y underscore pred. So after executing this line of code, we can see this is our array that's of our prediction, and y underscore test is the actual value. Now let's compare both the values. So as you can see here, our model make a prediction of around like 1,03,015, and actual value is around like 1,03,282. It's a quite great prediction. Now similarly, as you can see, its second value is around prediction is around like 1,32,000, and actual value is around like 1,44,000. Now sometimes it also make low predictions, I mean less accurate predictions, such as here it make a prediction of like 1,78,000, but actual value is around like 1,91,000. So it makes quite less progress. I mean, it makes great predictions sometimes, but sometimes also less predictions, I mean less accurate predictions. So that's it for our prediction. Now our model is going to make quite great prediction or quite accurate prediction sometimes, but sometimes it's also going to make less accurate predictions, or they're going to be very low and very high difference between the actual value and the predicted value. Why is that? Now in order to understand that, we need to understand that if there is a data set with multiple independent variables, so it's not always true that all the independent variables have relation with our dependent variable. It also be possible that there may be few very independent variables that doesn't have any relation with our dependent variable. So we need to remove those independent variables. That's going to increase our model's accuracy, because these variables may affect our model, and that may lead to the less accurate predictions. So in order to understand the concept, we are going to use this in our code. We are going to use states model API for that. Now this API is used to gain statistic information and understanding about our model and our variables, and then we are going to check whether there is a relation between this independent variable with our dependent variable or not, and how much strong it is related. If it's related, then we are going to use that variable in our model, and if they are not related, then we are not going to use that model. So let's start it in our code. Now we are going to import states model.formula.api first as an alias sm, and then we are going to create a new independent array of independent variable, because we know that there is a constant variable also in our multiple linear regression, that is b0, and that's not available in our training data or available in our independent variable. So we are going to create a column of a constant that is going to be value 1. So we are going to create a column of 1 and then going to append it into our independent variable x. So we are going to use independent variable x equals to, and going to use append function of numpy np.append, and then we are going to pass first array as np.ones, which is going to be a size of same as the size of x, that is around like 50 rows, and then we are going to use dot as type is equals to int. So we are going to convert the numpy array of ones into with all the values as integer, and then we are going to pass the value is equals to x, and that is our second array, that is our independent variable, and then we are appending both the arrays together on axis 1, that is column wise. So after executing this line of code, you can see that in our independent variable x, there is now a column of ones of around 50 rows, that is from index 0 to 49. Now after that, we are going to use a states model API and to get summary of our model. In order to do that, we are going to import a states model API first, like this. So in backward elimination, first we are going to access all the independent variables first, including constant, and then we are going to remove all the independent variable one by one, which are not having any relation with our dependent variable or having very less relation with our dependent variable. And we are keep doing this one by one by removing one column or one independent variable at a time from our x, until we get an collection of independent variables, I mean independent variable array x, which having those variables which have quite great relation with our dependent variable y. Similarly, in forward selection, we are going to start with one independent variable, and we are going to keep comparing its more accuracy, or we are going to keep comparing its relation with our dependent variable. If it is related to, if it's quite related with our dependent variable, then we are going to let it stay in our independent variable, and then we are going to add another independent variable, and then we are going to compare the relation of second variable with our independent variable and check whether they are high related or not. And similarly, we are keep going to do that until we get a collection of independent variables which are having quite great relation with dependent variable, and that's how we are going to get all the independent variables which are required for our model. And when we are going to use those independent variables for our model construction, then that model is going to give us quite great accurate predictions. So let's try to see both the methods, backward elimination and forward selection, in our code. Now in backward elimination, we are going to create a collection of all the independent variables first. So we created a new variable x optional, that is an independent variable, collection of independent variable, and then we are going to use np.array, and then going to pass first x with colon, that means all the rows of independent variable x, and then after that we are going to pass a list of all the columns or all the independent variables that we are going to use. So it's in x, there are around like 6 columns, that is from 0 to 5. These are the independent variables, so we are going to use them. So it's 0 1 2 3 4 5, so we are going to use 0 1 2 3 4 5, and then we are going to assign d type is equals to 4. It is required because as you can see, our array is of type object, and we can't access the array of type object here. We need to convert it into a float, so we are going to use d type equals to float. So after executing this line of code, as you can see, we get x optional with all the columns of our x and all the rows of x, and with a data type of float, array of float 64, as you can see here. Now after that, we are going to use a states model API and its function.ols. So as you can see, first we created an object of ols, regressor underscore ols, and then we passed sm1.ols, and in it we used two required arguments, that is ndog and xdog. Ndog is our for dependent variable and xdog is for independent variable. So in ndog we passed y, and in xdog we passed x optional, that is our new independent variable collection, and then we use .fit function to fit into our regressor underscore ols states model API. Now after executing this line of code, you can see that we got an object regressor underscore ols of states model API and then we use fit more function to fit it into our model. After that, we use regressor underscore ols dot fit summary function to get the summary of our model. Now as you can see here, there are around like 6 columns, 1 2 3 4 5 6. The first one is the constant, that is all ones, and all the other are our variables, our independent variables, which as you can see here, it is one R&D spend, administration, marketing, and these two are state in one hot encoding format. Now, and for backward elimination, we need to set a threshold value for a relation, and that let's say that we have set a threshold value of around like 0.5, 0.5. So we need to compare this value pre greater than modulo of t, and we are going to compare all the values with 0.5 and find out the biggest value which is greater than 0.5. So as you can see, this is our 0.990, that is greater than 0.5 and the greatest value here. So we are going to remove this column from our model because it is very less related for it. So as you can see here in X optional, the fifth column, the fifth independent variable that's having relation 0.099, that is quite more than our threshold value, and we that is like pre greater than modulo of t quite denotes like difference between the values, whether they are, if the value is more high, that means the less the relation between them. If the value is quite less, that means higher the relation between them. So as you can see, this is 0.99, it's quite high, that means there is very less relation between this independent variable with our dependent variable. So we are not going to use this in one model. So we are going to remove the fifth column from our X optional set, and now we are going to again execute this line of code, and then we are going to check the summary again. Now after that, for comparing all the values of threshold value 0.5, 0.94 is quite high, so it's also not related with our dependent variable. So we are going to remove the fourth column also. So let's remove the fourth column here. Now after that, we are going to execute these line of code again. Now in the new summary, we can see that 0.62 is the highest value and it's greater than our threshold value, that is 0.5. So we are going to remove this column also, that is second. So we are going to remove the second column from our collection, and then we are going to execute this line of code. Now after that, as you can see, I mean all the independent variables have less value of this and less than our threshold value. That means they are going to have high relation with our dependent variable y. So now as you can see here, we have remaining 0, 1 and 3 columns. So if we are going to use these 3 columns for fitting of our model or for training of our model, then the prediction that the model is going to make will be quite high compared to the previous one. Now this is all about backward elimination. Now we are going to start with forward selection. Now in forward selection, we are going to start with one column, I mean with any one of the column of our independent variable collection. So let's start with 0, and we are going to use the same code again, just we are going to pass here column 0, and then we are going to access its summary. So after that, as we are going to execute this code, you can see in the summary the value of p is 0.000, that is less than our 0.5. So it is related to the model, it is related with our dependent variable. So now we are going to add another column, that let's say we add column 1. Now after accessing its summary, you can see column 1 is also having 0.000, so it's also related to the dependent variable. So let's add another column 2. So after executing this line of code, we can see it's going to return 0.289. So comparing it to the threshold value 0.5, it's okay. So we are going to let it stay right now. Now we are going to add another variable, that let's say of column 3. Now let's execute this line of code. Now in this summary, you can see that on all the values, after us adding another independent variable, you can see that it shows that the dependent variable of column 2 makes a difference, I mean makes a value of p greater than mod t equals to 0.6, which is more and greater than our threshold value 0.5. So that states that the column 2 is not related to our dependent variable much. So we are going to remove the column 2 from here, and then now we are going to add column 4. So let's add it and access the summary of our model. As you can see here, it's also having value more than 0.95. Now note it states third because for the collection it's on the third index, but here at the third index it's 4. So we are going to remove the 4 from here, and then let's add column 5. That's the last column, and let's see summary. Now here you can see that its value is quite greater than 0.5. That means it's also not related to our dependent variable, so we are going to remove it. It states x3, that's the the independent variable. You may have seen the equation that are constant b0 and then x1, x2, x3. Those are our independent variables. So here at x3 position it's our fifth column, so we are going to remove it too. Now there are no any other columns remain, so we can see that both the equation led us to the columns of 0, 1 and 3 of independent variable. Now if we only use these three columns 0, 1 and 3 for fitting of our model over training set, then after that when we apply prediction over testing set, then it's going to make quite great prediction compared to the previous model. That's it for our today's session.
Hi everyone. Today we will learn about polynomial regression. So let's start with what is polynomial regression. Polynomial regression is a form of regression analysis, and it's also a one kind of regression technique. Now, as you all know, when there is a linear relation between our independent variable x and dependent variable y, we use linear regression model. But what if the relationship is non-linear or somewhat a parabolic relationship between x and y? Then at this situation, polynomial regression comes handy. Now let's see a small difference between linear regression and polynomial regression. Now as you can see in this plot, these data points are in a linear fashion, and the given equation y equal to b0 plus b1 x1 is a linear equation. So when we draw a line with this equation, we can see that the line will satisfy all the data points in the plot. Now let's see another example. Now in this plot you can see the data points are not in a linear fashion but are somewhat in parabolic path. So when we apply the same linear line here, the line will not satisfy this data point evenly as it satisfied in the previous case. So to avoid this problem, we use polynomial regression. So let's see how polynomial regression will helps in this. So now as you can see, the equation y equal to b0 plus b1 x1 plus b2 x1 square, the curve made by this equation will satisfy all the data points in the plots and solve our problem. So so when the data points are not in linear relationship but in a non-linear relationship, then polynomial regression is very useful. Now let's see the equation we have learned so far. Now the simple linear regression y is equal to b0 plus b1x, multiple linear regression equation y equal to b0 plus b1x1 plus b2x2 up to bn xn, and polynomial regression equation which is y equal to b0 plus b1x1 plus b2x1 square up to bn x1 raised to n. Now let's have some look on polynomial equation degrees. When the degree of polynomial equation is 0, then y is equal to constant. When the polynomial degree equal to 1, then y is equal to mx raised to 1 plus c. When polynomial degree is 2, y is equal to ax raised to 2 plus bx plus c. Now let's go for the implementation of code. So let's start with coding part. In this, the first step is importing libraries. So the necessary libraries that we need are NumPy, Matplotlib, and Pandas. The second step is to import our data set and split our data set into feature of metric x and dependent vector y. So let's first import our data set. So dataset equal to pd.read underscore csv, and the name of our dataset is position underscore salaries.csv. So let's first run this code and go through our data sets. So here it is our data set, and it has three columns: position, levels associated with the positions, and salary. And in this algorithm we will use level and salary column. The level column will be our feature of metric x, and the salary column will be our dependent vector y. So let's split them into x and y. So x is equal to dataset.ilog colon comma 1 colon 2, So as the level column is in at index of 1, so we need that column. That's why we had written here 1 colon 2 dot values, and the y is equal to dataset dot ilog colon comma 2, which means the salary column is at index 2, so that's why we written here 2 dot values. Now, as you know that the data set consists of only 10 rows, so it's a very small data set. It's only for learning purpose. So there is no need of splitting this data set into training and test sets. That's why I'm skipping this step here. Now, as you know that in theoretical part also, I gave you a little differentiation between linear regression and polynomial regression. So in this coding part also, I'm giving you a small bit of difference between a linear regression model and a polynomial regression model. So let's first start with the linear regression model. For this model, we are going to use sklearn library. So from sklearn.linear model, we are importing linear regression class. Now we have to make an object for this class and initialize the object. So lin underscore reg equal to linear regression class. So now our object is initialized. Now we have to fit our object to the data set. So lin underscore reg dot fit x comma y will fit our object to data set. And now let's run these lines of code so that our model will be formed. So now our linear model is formed. Now let's go with the polynomial regression model. So for polynomial regression also we are using sklearn library. So from sklearn.preprocessing we are importing polynomial features. So for this class also we have to make an object and initialize the object. So poly underscore reg equal to polynomial features, and in this we are passing a single argument, that is degree, and this degree represents the highest degree of polynomial features. So here we are putting the value of degree equal to 4. Now, in linear regression model, we are using the feature of matrix X, which consists of only a single column of levels. But in polynomial features of degree 4, we need 4 separate columns representing each degree for our model to be trained. So for this, we have to make another feature of matrix. So for this, we are writing code x underscore poly equal to poly underscore reg dot fit underscore transform x. This code will transform our feature of matrix X into 4 columns feature of matrix, which each column having different degree values. So let's run these 3 lines of code. Now, as you can see that it consists of the 4 rows. The first is the original, the second is the power of 2, the third is power of 3, and the fourth is power of 4, and the fifth column, which is the column of constant c. So now after that, for building the polynomial model, we need the regression model class only, but instead of passing the feature of matrix X, we will pass the X poly matrix that we form now. So let's run these 2 lines of code. In this, here we made another object of linear regression class, the lin underscore reg2 equal to linear regression, and now we are fitting this object to our new feature of matrix and y. So let's run these 2 lines of code also. So now our polynomial model is also formed. Now after this, we have to visualize what we have made. So let's first visualize the results of linear regression model. So for this, we are using matplotlib library. So first we have to plot our data points. So for this, we are using plt.scatter x comma y and with a color equal to red. After that, we have to plot the prediction line. So for this, we are using plt.plot x comma lin underscore reg dot predict x. Ling underscore reg dot predict x will predict the values of salaries for the given matrix X, and we are providing its color equal to blue. Now after that, we are giving a title to our plot, which is truth or bluff, and the X label is position level and the Y label is salary, and plt.show will show our graph. So let's run this code. Now As you can see, this is our plot. The data points are not in linear fashion, they are in non-linear relationship, and our line is linear, and which is not satisfying the data points evenly, and this will produce a wrong or a result of our prediction. So let's now visualize the polynomial regression results. For this also, the change is only the predict function. Here the linreg to object is used with dot predict method, and we will pass polyreg.fit transform x here instead of poly x, because poly x poly has already the value of features x, but we want a new features of matrix. That's why we are using polyreg.fit underscore transform instead of x poly. So let's run this code also. Now you can see that all the points are covered by our polynomial curve, and in this our accuracy is very much high. So now predicting a new result with linear regression model. In this we are using object lin underscore reg dot predict and double square bracket 6. 6 is the number of level. So let's run this code. Now we are getting 2,89,939 as our answer. Let's compare it with the y at level 6. Now you can see it's 22 lakh and we are getting 2,89,000. So it's way beyond the original data. Now let's see what we get from polynomial regression prediction. So let's run this code. Now we are getting 1,43,000, which is very much close to the value 2 lakh. So and the value is in this also, the value is differ from the original value because the data set is very small. If the data set is quite large, then the answer will be very much close to the 20,000. So thank you for listening this session. Hi everyone, today we will learn about decision tree regression. So let's first see what is decision tree. So as you can see, a decision tree is a flowchart like tree structure where each internal node denotes a test on an attribute. Each branch represents an outcome of the test and each leaf node holds a class label. So as you are all familiar with the flowchart, which consists of a root node and several internal nodes, and at the last level there are leaf nodes, and all of these nodes are connected with branches. So in this definition of decision tree, we are saying that all the internal nodes represents the test cases that we apply on our data sets, and the branches that are coming out from these test cases denotes the outcome of the test case, whether the test is passed by a data point or failed. And then the outcome branch comes in a leaf node which represents the label for the data class, for example that this data is belong to class A or class B, etc. Now here as you can see the term CART, C-A-R-T, which represents classification trees and regression trees, because decision trees can both be used in classifications and regression. So in this session we are learning about regression trees. So let's see a example plot of data points which are plotted in x and y axis. So as the plot is given here, now that as you can clearly see that the points are not in a linear relationship, they all are randomly scattered and are non-linearly related to each other. So for this, the decision tree will apply its algorithm and split the data sets into different regions. So let's see how it splits the data sets. So now as you can see, it splits into 4 types. The first split is at x-axis 20. The second split is at y-axis 170. the third split is at 200, and the fourth split is at 40. So the four splits will form 5 different regions. Now after splitting, the decision tree will calculate the average of each region, and the average will act as a label for the regions. So let's see a decision tree flowchart. Now as you can see, the root node, the several internal nodes, and the end are the leaf nodes, which represents the average value as the labels. So as you can see that when the suppose x1 at a particular value, if it's less than 20, then the outcome is yes, and we goes to the next internal node. If the in this case also, if the outcome is yes, then we get the label 300.5, which belongs to a particular region. So this is the final task done by decision tree by assigning the average value to each regions. So when we predict some values, the average value is calculated, and if the value is near about these average value, then the algorithm will predict that this data point is belong to this particular region. So I hope that the basic concepts of decision tree are clear to you all. Now let's move to the implementation part of the decision tree algorithm. So let's get started with the implementation part. And the first step, as always, you know, we are importing the libraries, and the three libraries are NumPy, Matplotlib, and Pandas. After that, we are importing our dataset, which for which we are using pd.read_csv, and the name of our dataset is position_salaries. So let's first run these lines of code. Now as you can see, this is our dataset, consists of 3 columns: positions, level, and salary. In this datasets, we are using level column as our feature of matrix X and salary as our independent variable Y. So let's write these 2 lines of code. Now as you can see, this is our feature of matrix X, consists of all the 10 levels, and the Y consists of all the salaries associated with the levels. Now after that, we will fit our model. In this algorithm step, I'm not using splitting our dataset into train and test case, because our datasets consist of only 10 rows, so there is no meaning of splitting this. And I'm also not using feature scaling, because the library which we are using for our model already transform our columns into featured values, so that's why we don't have to explicitly feature scales our value. That's why I'm directly coming to the step where I'm fitting a model. So for this, we are using sklearn.tree module, and from that module we are importing decision tree regressor class. Now after importing our class, we have to make an object for our class. So we are initializing our object regressor equal to decision tree regressor, and we are passing only one argument, which is random state. Now random state here is the seed value for our randomized number. So and the value for random state can be any integer value. So the main reason of using this random state parameter is that every time we run our code, we get the same randomized value as we get in our previous code. So that's why we are using random state here. Now after that, we are fitting our model. So regressor.fit the feature of matrix X and the dependent variable Y. So let's run these code. So now our model is trained. Now let's predict a new value, which is 6.5, the value of level, which we never trained our model with. So let's run this code and see what we get. Now as you can see, we are getting 1,50,000. Now let's compare it with our data set. So for level 6, we are getting the salary 1,50,000, and here we are predicting for 6.5, so it's very much close. So now let's visualize what we are doing here. So this is our plot. But as you can see that I told you earlier in the basic concepts that the decision tree algo will calculate the average for each interval or region. So here there's supposed to be a horizontal line parallel to our x-axis, but instead of that all points are joined by a straight line and forming a curve. So this is the wrong plot of decision tree. So to correct it, we are going to use a higher resolution for plotting. So I'm uncommenting these two lines, and you will see the difference after implementing these two lines. So I'm running this whole code once more. Now you can see very well that at each interval there is a same value because the average will be same for whole interval. So interval 1, interval 2, interval 3, so on, interval 10. So that's all for decision tree. Thank you very much for listening. Hi everyone. In today's session, we will learn about random forest regression. So as we discussed earlier about decision tree regression, in which a single tree is used to split our data set and calculate the average value of each splitted region. But as the name suggests, random forest, a forest is a collection of trees. So a random forest regression is also the collection of decision tree regressions, and there are several different decision trees which will predict the output for the same dependent variable y, and thus we are getting average of all the decision tree predictions, and thus the answer is more precise and accurate than the decision tree regression which only uses a single tree. So let's start with the random forest regression. As the first step, importing libraries. The second step is importing data sets. And so let me first run this code up to importing our data set. So our data set is imported, as you can see. Now, since the data set is the similar as the ones I have discussed in previous videos, so I'm not going to split this data set into smaller train and test cases. So let's start going to the step where I'm using the random forest model. So for this also I'm using a sklearn module, in which the sklearn.assemble module is used. In this, from this module, I'm importing random forest regressor class. Now as the class is imported, now we have to initialize the object for its class. So regressor is the name of object which is equal to random forest regressor class, and in this class we are going to pass two arguments. The number one is n estimators, which is none other than the number of trees we are going to require, and the second is the random state, which is for random numbers. So now after importing our class, now we have to fit our model. So regressor dot fit x comma y. So I'm running this code of our model. So our code is run, and in this code I'm giving the n estimator values equal to 300. After that I will visualize the code and let's see what it will give us. So as you can see, the graph is similar to the decision tree, but in this this number of steps are more than the decision tree, because there are several number of decision tree which are predicting the value for dependent variable y. So the steps are also increased. Now let's predict the value for level 6.5. As you can see, I'm getting a very much closer answer in this algorithm other than the previous algorithms we are learning. So random forest is accurate algorithm for this data sets. So thank you for listening this session.
Hello friends, welcome to the course on machine learning. Today we are going to start with a new topic, that is classification. Now before this we have seen regression, what is regression, different types of regression and their implementation in code. Now we are going to start with classification. What is classification? Classification is all about like classifying things on the basis of input features there can be various data like the text, and we have to classify whether the email is spam or not, or like it can be images and we have to classify whether the image is of a cat or a dog or a person, and things like that. So we are going to start with a new concept of classification, and we are going to start with the simplest one, which is logistic regression. Now you may think that it is classification, then the why name is like logistic regression. So the concept of logistic regression is similar to our regression like multiple linear regression, but it's all the change is that the dependent variable y, or I mean the outcome, is going to be a categorical value instead of a numerical value. For example, like we can see whether a basis of input features like input features of tumor, like the size of tumor, shape of tumor, and its position and things like that, and we are going to predict whether the tumor is malignant or not. Now let's dive into the intuition behind the logistic regression. First, let's say we want to classify whether the user having specific age took an action on an advertisement or not. And so let's say here, as you can see, that there are various data points of age available in the graph, as you can see from here to here, and 0 is for the user didn't take any action, and 1 for that the user took any action on the advertisement, like on purchase the item or click on the advertisement or something like that. So let's say if we implement a simple linear regression over it, or like multiple linear regression over it, so it's going to plot a straight line, I mean plot a best fitting line of model, as you can see here, but it's going to predict a value that will be like 0, 1 and 0.5, 0.75, 1.2. As you can see, the values can be more than 1 and values can be less than 1. So in order to overcome this, we can put now we can think of it like putting certain conditions, like if the value is more than 1, then it will be 1, and if the value is less than 0, then we can make it to 0. But as you can see, the model's accuracy will be very low because this straight line is not I mean it's not going to fit over the data points, and the error will be a lot between them. So the logistic regression is going to put a curve between the data points in such a way that it will fit over the data point, and it will generate the minimum error from data points and the model fitting line. Now as you can see, this green line, that is a curve, and it will be like this. So it's going to fit the data points as much as possible, and our logistic regression model is going to predict not the values, but it's going to predict the probability. Like the probability of taking an action will be 0.7, here it will be like 23%, it will be like 85%, and here it will be like 99%, and things like that. And it's going to be between the range of 0 and 1. Now we can set a threshold value between the probabilities, like setting a threshold value of probability of 0.5, and we are going to make it like if the value probability is less than 0.5, then it's going to be treated as 0, and if the value of probability is more than 0.5, then it's going to be treated as 1. And in such a way, we are going to make a prediction model which is going to make prediction of the outcome like 0 or 1, or like whether the user took action or not. So as you can see in this image, we have like y prediction and x variable, and you can see we have a threshold of around like 0.5, and all the data points that are below the 0.5 values, like here, it's going to make prediction y hat equals to 0, and all the value above this threshold value are going to treat it as y hat is equal to 1. So that's it behind the intuition of logistic regression. So let's see it in our code. So first, we are going to start by importing the required libraries, that is NumPy and Pandas. And then we are going to import our dataset. Here we are going to use this social network ads dataset, where there is a various columns such as user ID, gender, age, estimated salary, and purchased. This dataset is about the user with gender, their age, and their salary, and purchase is for like whether after seeing the ad they purchase the item or not. 0 that the user didn't purchase the item, and 1 for the user that purchased the item. So we are going to start implementing logistic regression on this dataset. So let's dive in. First we import the data set. As you can see, we created a data frame named dataset using pandas and using its function .read csv, in which we pass the dataset file, that is social network ads.csv. Now all the files will be available in the description. So let's create our data frame. As you can see, this is the data frame that we just created: user ID, gender, age, salary, and purchase. Now here our dependent variable will be purchase, that will be our y, and 0 for not purchase and 1 for the purchase. And we can use independent variables from these. Now the user ID of all the users will be different, and they are not going to be related with our dependent variable y, that is purchase, so we are not going to use it. And there's not going to be relation between the gender and its purchase. I mean, there's not going to be a relation between gender and purchase, because it's not going to depend that if it's male, then it's going to purchase the item, or if it's female, it's going to purchase the item. So we are only going to use two independent variables, that is going to be age and its estimated salary. So let's create our independent variable x using dataset.ilog, and here we specify colon for all the rows and 2:4 for columns from 2 to 4 but exclusive of 4, so that it will be at index 2 and 3, that's our age and salary. And after that we are going to create our dependent variable y using dataset.ilog, and we specified here first colon for all the rows and -1 for the last column, and use dot values to make it an array. Now after executing this two line of code, we can see that we created two variables, that is our independent variable x, that is age and salary, and our dependent variable y, that is purchase. Now first we are going to split it into a training data and testing data. So we are going to import sklearn.model selection, and we are going to import train test split function. You may have seen this before in the previous sessions. Now we are going to create four variables, that is xtrain, xtest, ytrain, and ytest, that is our training set and testing set. And then we are going to use train_test_split function, where we are going to pass x and y, our dependent variable and independent variable, and then we are going to pass test size, that is going to be the size of testing data, and then random state for not picking random values instead of going from index 0 to end of rows. So after executing this line of code, you can see that we created four variables: xtrain, xtest, ytrain, and ytest. Here as you can see, the value of age is way too less compared to the salary, so our model is going to make it like the value of salary is way too much compared to the age, so it's going to use a salary for making most of the prediction, because the value is huge, and it's going to make it like the most of the difference, or like most of the relation is on the basis of salary. We don't want to do that, because it's going to reduce the accuracy of our model. So we are going to apply feature scaling on it, and by applying the feature scaling on this, the values will be like comparatively equal or like nearly equal, so they can be used to fit our model, and that's going to make prediction much more accurate compared to the normal one. Now we are going to apply feature scaling on it, so that we are going to import first from sklearn.preprocessing, and then we are going to import standard scalar class, and then we created a sc_x object of standard scalar class. Now we are going to apply feature scaling on our training data and testing data of independent variable. So first let's on in the training data xtrain, and then we use sc_x and its function fit_transform, and then we pass training data. So after executing this line of code, you can see that we created a x_train and applied feature scaling in it. Now after that, we are going to apply feature scaling on our testing data of independent variable. So xtest, so we are going to assign the values to xtest, and then we use sc_x and use .transform, just only transform, because we already fitted it into the variable x_train. So we are going to use sc_x .transform function, and then we are going to pass x_test. So it's only going to apply feature scaling on testing data. So after executing this line of code, we are going to have a new feature scale testing set of independent variables. Now we are going to apply logistic regression and we are going to create our model. So first we are going to import logistic regression class from sklearn.linear model. After that we are going to create an object named classifier, and we are going to create it as an object of logistic regression class, and we are going to pass random state is equals to 0, so it's not going to pick random data points for making model. So after executing this line of code, you can see we created an object, we created our classifier model of logistic regression. Now after that we need to first fit it into our training set, so we are going to use classified.fit function, and then we are going to pass x_train and y_train. So this is going to fit our model with training set. Now we need to make prediction on testing set. So we are going to use y_predict is equals to classifier.predict and x_test. After executing this line of code, you can see we created a variable y_predict, and this is the prediction that our model made, and we also have y_test available, that is the actual value, and these are the predictions. So we can compare the values from it, like 0 0 0 0 0 0 1 0. Here it makes an error, here it makes prediction of 1, well actual value is around like 0. So in order to check the accuracy of our model, we are going to use confusion matrix. So we are going to use confusion matrix. You may not be familiar with confusion matrix, so first let's create our confusion matrix, and then we are going to see how it works and what this is all about. So first we are going to import confusion matrix class from sklearn.matrix. After that we are going to create a confusion matrix named CM using confusion matrix, and then we are going to pass both the values, that is the actual value of our testing set and the prediction of our testing set. So after that it's going to make a matrix. Now this is a matrix. Now here the above 0 1 is about the actual values of our testing set, and this value on the left hand side, that is 0 and 1, this is about the testing predictions, the prediction made on the testing set. Now this confusion matrix defines that the actual value of there is around like 65 actual values, that is 0, and our model makes a current prediction of 0, and there is around like 24 values, actual value, that is 1, that is for purchase, and our actual model also make the prediction of 1 for them. But there are 3 values, there are 3 actual values where the values were 1 and our model make a prediction of 0, and there were around like 8 values where the actual value were 0 but our model make a prediction of 1. So in this way we can see the actual we can see our accuracy and like how accurate our model makes predictions. Like it make a prediction around 65 true for 0 values and 24 true for 1 value, and make a error in 8 values where the actual value was 0 and make prediction 1, and where the actual value was 1 for and made prediction 0. So in this way we can see our accuracy of our model. We can also calculate it using by adding these true values that model make prediction, that is 65 plus 24, and we can divide it by our total number of rows, that is 100. In our testing set the total number of rows is 100, so let's compute it. It makes prediction 64 plus 25 true, that is around like 89, and then divide by 100, so it's making an accuracy of around like 89%. So that's it for our today's session. Hello friends, welcome to the course on machine learning. Today we are going to start with a new concept, that is SVR, which is referred as support vector regression. Now we are going to start with have a basic understanding of what is support vector regression, how it works and like that, and then we are going to implement it into our code. So let's dive in. First we are going to start with its intuition. Now as you all remember, what is simple linear regression? Now simple linear regression always try to fit the model on data set in such a way that it reduces the error rate as minimum as possible. Now, SVR support vector regression works a little different. It tries to fit the line with a minimum error rate, but also try to fit the model on dataset in such a way that the error rates should be in a margin, or I mean the margin of or threshold for the error rate will be as minimum as possible. Now it can quite here a little complicated first, but we are going to see here. As you can see, let's say there are 4 data points here. These, as you can see, the green 4 data points. Now SVR tries to fit a line over these data points in such a way that the error rates between the data points and the present model line will be as minimum as possible, and also it will try to fit the line in such a way that the margin for or the threshold for the error rate will be as minimum as possible. So this is all the basic understanding of SVR. So we are going to start implement it in our code. We are going to start by importing our basic libraries, which is as NumPy, Matplotlib and Pandas. After that, we are going to import our dataset. We are going to create a data frame name dataset using Pandas library, and then we are going to use read_csv function to import our dataset from a CSV file. Now we are going to use a position_salaries.csv file. This is the dataset that we are going to use. All the links are available in our description. Now there are 3 columns, as you can see: position, level and salary. Position is the job position that are available in the company, and level are assigned like a level number to each position from lower to higher, and then it's represented salary as level salary for a level 1 job is around like 45,000, and for level 2 it's around like 50,000, and like that. We are going to use SVR to create a machine learning model that is going to predict the salary for a certain level of job, so and which can be used, for example, in like a recruitment. When a new person apply for an interview or for a job, I worked at the level or a position at this and have had the salary around like this. So in this way the company will, or I mean the recruiters will know that the person is bluffing or telling the truth, because they will have a machine learning model which will predict the salary of the certain level. Now we are going to implement the model in our code. So first we are going to import a data set. Now as you can see here, this is a data frame that we created as a data set. Now we only need the two variables from here. First is the independent variable, that is level, and second is the salary, that going to be our independent variable. So first we are going to create our independent variable x using dataframe.ilog method, and then in the square bracket we are going to pass colon for all the rows, and then we are going to pass from starting index to the ending index. So here in our data frame, starting index is level 1 because we required the level for our independent variable, and then ending index will be for -1 because we doesn't require the last column of our data frame. So it's going to return an array only of level from 1 to 10. So let's try to execute this line of code. As you can see here, this is, we created an independent variable x of a column level of our data frame. Now we are going to create an dependent variable that is going to be y, and that's going to be the last column. So we created y equals to dataset.ilog, and then we use past colon for all the rows, and then comma -1 for the last column of our data frame. So executing this line of code, you can see that we created an independent variable y, and that's all about the salary from a data frame. But as you can see here, the size or shape of y is 10, that's a vector. We require it to be an array. So we are going to reshape our variable, dependent variable y. So we are using y equals to y.reshape. We are going to use y is equal to y.reshape, and then in reshape we are going to pass the new shape that is going to be length of y, 1. So it's going to create a 1 column array. Now as you can see here, the size changes from 10, to 10, 1. Now after that we are going to pre-process our data set. As you can see here in data set, both the variables, independent variable and dependent variable, have a huge difference between them, from like 1 to 45,000, 2 to 50,000. And now if you try to create a model that's going to fit over the data set, so it's going to relate that the salary is way more greater than the level, so it's going to assign the coefficient for level, from coefficient like b1, as you all remember the equation, which is y is equal to b0 plus b1 x1, where x1 is our only independent variable here, that is level. So the assigned coefficient b0 will be, the value of assigned coefficient b0 will be way more huge, so that it can be used for creating a relation between level and salary, and that's going to make a model a little inaccurate. So we are going to apply feature scaling. Now we have seen the concept of feature scaling in data pre-processing section. So we are just going to implement the process of feature scaling. So we are going to start with the importing the standard scalar from scalar.preprocessing, and then we are going to create two different objects for independent variables, so that we can pre-process both, so that we can pre-process or I mean apply feature scaling to both the variables and independent variable x and y. So we are going to create two objects of standard scalar. Now after that, as you can see here, we created two variables scx and scy. We are going to use these two variables to apply feature scaling on our dependent variable y and independent variable x. So let's do this. As you can see here, we use x equals to, and the object we use created for our independent variable sc underscore x, and we use its function fit underscore transform and pass the independent variable x. So it's going to apply feature scaling on x and then return the output to the x. And similarly, the next line of code is going to apply feature scaling on y and going to return the output, and which is going to be stored in the variable y. Now as you can see here, now our independent variable x is all feature scaled, and our dependent variable y is also feature scaled. So for creation of model, we are going to import svr class from sklearn.svm package. After that, we are going to create an object for regressor of our svr class, in which we are going to pass kernel is equal to rbf. Now kernel are the approaches how the model is going to fit the training data over the line, or I mean how the model is going to fit itself. We are not going to go deeper inside the understanding of kernel, so we are going to use kernel is equal to rbf. rbf stands for radial basic function, and there are other kernels as well, such as linear, non-linear, and like Gaussian, and also others. So let's create our model and create a regressor by executing this line of code. Now we created a regressor of svr regression. Now we created our model. We are going to fit it in our data, that is x and y. As we have limited amount of data, so we are going to fit the model on the whole data. So we are going to use regressor.fit function and going to pass the data variables, which is independent variable and dependent variable x and y. After fitting it into our data, let's try to make a prediction for around like level 6. First we use sc underscore x dot transform, so that we can apply feature scale to the input that we are passing here. So it's going to be passed into a model in a feature scaled manner. So we, as you can see here, we created an 2D array from two square brackets, and inside we passed value 6, and then we passed it to the standard scalar object for independent variable, and then used dot transform to apply feature scaling on the value 6, and then we used a regressor.predict function so that we can make a prediction on the value. And now the output will be also in the feature scale manner, so we are going to inverse transform it back to our value. So we are going to use the object of standard scalar for dependent variable, and going to use dot inverse transform function, and then going to assign the value that's going to be returned from the prediction. So this is going to make prediction for the value level 6, and going to return the salary at the level 6. So as you can see here, it make a prediction of salary of around like 1,45,000. So let's see in our data set. For level 6, the salary is around like 1,50,000. So it's make a quite great prediction. Now after that, let's try to visualize it in our code. So first, we are going to scatter the data points, and then we are going to plot our model by its prediction. So let's try it. First we use plt.scatter to make scatter of data points, and then we passed x and y. Now as you may have remember, we have applied a feature scaling over x and y, so we are going to inverse transform back them to their original values. So we are going to use the respective standard scalar object scx and scy, and then going to use inverse transform function to transform them back to their original values, and then we are going to pass x and y into them. And let's say we assign a color equals to red for the scatter. Now let's make plot for our predictions. So we are going to use plt.plot. Now similarly, as you can see here, we did the same thing. We passed an independent variable x into an inverse transform function of standard scalar object for the x, and then we are going to pass the prediction of for the following x. So we are going to make our model regressor.predict function, and then we are going to pass x inside it, and then we are going to make a plot over the prediction. So we need to inverse transform it back to the original value of dependent variable. So we are going to use sc_y and dot inverse transform function over its prediction, and then let's say we assign the color equals to blue for this. Let's say we assigned a title for our plot, and then we assigned x label and y label for the x-axis and y-axis, and let's say we use plt.saw to display our plot. Now as you can see here, this is a plot that we just created. As you can see, this is the position level, this is the salary, and these are the data points that are available here, and the blue lines are the line for our model prediction from starting to index. As you can see, for the last position, it's not making quite great prediction because there will be a huge error rate. Now it's because that we used RBF kernel. Now RBF kernel uses method to fit the data point by using its neighbor data points also. So to fit this data point, it's going to use its neighboring data points, which will be this and this. But for this, the next neighboring data point is not available, so it's not going to fit the line over it quite well. Now after that, as you can see, these lines are kind of straight. We need in order to increase the dimension or increase the resolution for the curve, we are going to use a new method. Now first we are going to create a new array xgrid, and then which will going to be created from np.arrange function, in which we are going to pass a range of x, which will be minimum of x and maximum of x, and we use the same inverse transform method so that we can apply inverse transform to the feature scale variables. So it's going to create a array from minimum value to the maximum value with a difference of 0.1. So after executing this line of code, as you can see here, we created a variable xgrid from 1 to maximum value, which is 10, with a difference of 0.1, 1, 1.1, 1.2, 1.3, 1.4, and like that. And now we are going to use the same functions from above. I mean, we are going to make prediction over this instead of just x, as contains the value from 1 to 10. But we also, if we make a more prediction of around like 1.1, 1.2, 1.3, so model is going to make prediction for that level also, and there will be variation, so it will increase the resolution of our curve. So now as you can see, xgrid is then also a vector. Similar as we have did in the y, we have to reshape it. So we are going to use xgrid.reshape and then pass length of xgrid, comma 1. Now after executing this line of code, it's going to create a 2D array of one column with all the values from 1 to 10 with a difference of 0.1. Now after that, we are going to use the same, we are going to scatter the data points of our data set. So we are going to use plt.scatter, and then going to pass inverse transform of x and inverse transform of y, and we are going to set the color equals to red. After that, we are going to use plt.plot, and then we are going to use xgrid instead of x, and the xgrid is not feature scale, so we are going to use it as it is. So we are going to use xgrid now, but xgrid is not feature scale, so for making its prediction we need to apply feature scaling over it. So we are going to use the feature scaling of by using the object of standard scalar of x. So we are going to use sa._x and dot transform function to apply feature scale over xgrid, and then we are going to use regressor.predict function to make a prediction of the over the value, and then we are going to use, apply inverse transform over it so that we can get the prediction into an actual value of salary. So we are going to use sc_y.inverse transform to make prediction. Now after that, we are going to set the color equals to blue, and then we did the same. We assign title, x label and variable, and we use plt.sort for displaying of our model, I mean for the displaying of our plot. Now as you can see here, this is the second plot we created, and you can see these lines are now more curvy compared to the previous one, which are kind of straight, and it gives quite a better understanding compared to this of our model. Now that's it for our today's session.
Hi everyone. In today's session, we are going to learn about k-means clustering, which is a part of unsupervised learning. So if anyone of you have a doubt about what is supervised learning and unsupervised learning, then please refer to our webinar, which is on getting started with machine learning and clear your concepts. So let's begin with k-means clustering. So what is k-means clustering? So k-means algorithm is an interactive algorithm that tries to partition the dataset into k predefined distinct non-overlapping subgroups or clusters where each data point belongs to only one group. So in simple terms, k-means algorithm splits or partition our data sets into different subgroups or clusters, and each data point will belong to the different subgroup. So let's understand what is k-means. So let's suppose we have given this plot as an example data set. Now after applying k-means, we get something like this three clusters. So let's understand how this mechanism works. So this is a step-by-step explanation of k-means algorithm. So the step number one is choose the number k of clusters, and here we are taking k equal to 2. This is the arbitrary number. You can choose as much clusters as you want. So after this, the step 2, select at random k points the centroids. Now after choosing the number of clusters, we have to choose the number of centroids and randomly initialize them. So first of all, the centroids are the center of the point where the center of mass of the object exists. So these clusters are some kind of closed objects, so they have their center of mass. So we have to store their center of mass at centroids. So let's move to the step 3. Now assign each data point to the closest centroid. So for this we are going to use a little bit of mathematics. So for this we will join the two centroids and then draw a perpendicular line to the joining line, and the line will separate the points in two different clusters. So let's see. So here you can see that the line, the points above the line are colored in blue and the points below the line are colored in red, depicts the two clusters. Now after separating the clusters, now we have to calculate the center of mass of the cluster. So let's see the step 4, which is compute and place the new centroid of cluster. So after computed, the value is this dotted square. So let's move our centroid to this position. So after moving this our centroid to this position, now we have to reassign each data point to the new closest centroid. If any reassignment took place, go to step 4, otherwise go to finish. So now after this we have to again reassign our points. So we have to apply the same method, which is perpendicular line. So this method will continue till we get the exact position of our centroid. So we are continuing this step. So now we get the exact position of our centroid, so we will finish our model. So this is our final model with 2 clusters. So this is all about k-means algorithm and its mechanism. Now there is one problem in k-means algorithm, which is random initialization trap. So for an example, take this data sets. In this you can see from your eyes that it will form 3 clusters. So this is first initialization. So in this there are 2 clusters on right side and 1 cluster on left side, and the second initialization is of same data set, but here the left side consists of 2 clusters and right side consists of 1 cluster. So this randomization problem will affect your code. So to overcome this problem, the solution is k-means plus plus algorithm, and you don't have to study this algorithm, it's just the dependencies. So you have to just apply its dependency or import modules in Python and R language to use this model. Now after this there is one more problem, which is selecting the right number of clusters. So how can we select the right number of clusters? From this example data set, you can see from your eyes that the data sets will depict us to take 3 clusters, but it's a simple and small data sets. What happens if the data set is so large? So for this we have to need a method to select the number of clusters. So for this we will use WCSS, which is within cluster sum of square matrix, and the formula is given here, which is summation of distance between each and every point and its centroid, and then we have to square it. So let's see in example. So in this the data set is the previous data set only, but instead of 3 cluster we are for taking 1 cluster only. So C1 is the centroid of the cluster and PI are the data points. So we will calculate the distance of each data point from the centroid and then square them, and then after squaring them we will make summation of them. So the main concept of WCSS is that to choose the better number of clusters, the WCSS value should be less. So if we choose a single cluster, then the distance value will be very large. So to reduce this, we now going to choose 2 clusters. So these are our 2 clusters, C1 and C2 with the centroids. Now the same formula will be applied, but in this, instead of calculating for cluster 1, we will now add also the distance of cluster 2. So to reduce furthermore the value of WCSS, now we will choose cluster equal to 3 clusters. So this is the formula for 3 clusters. Now this is the data. So there is another method which is called elbow method, which is used with WCSS to depict the number of clusters. So you can see from here that when the number of cluster equal to 1, the WCSS value is 8000, and when we change the number of cluster from 1 to 2, the value drastically dropped to 3000. So you can see there is very sudden change in the WCSS value, and if we further change the number of cluster from 2 to 3, the values again drop till 100,000, and then after that it will decreasing with slow and steady pace. So we can see here that number of cluster equal to 3 will be our optimal choice, and you can also see that this plot is looking just like an R elbow. So you have to choose the point where the elbow depicts. So in this image you can see that 3 is the optimal number of clusters. So this is all about k-means algorithm, theoretical and conceptual part. Now we will move towards the implementation part. So let's start with the implementation part. So as always, our first step is importing the libraries. So let me run this code and import our libraries first. So now our 3 libraries are imported. After this, we will import our data set, which is mall customers.csv. So I'm running this code and importing our data set. So you can see that our data set is consist of 5 columns: customer ID, gender, age, annual income in thousand, and spending score in the range of 1 to 100. So we will require only the last 2 columns, which are annual income and spending score, for our feature of matrix X. So let's get these 2 rows. So the code for this is this. So now our feature of matrix is ready with the 2 columns that we wanted. Now after this, we have to decide the number of clusters we want for our algorithm. So for this, we will use the elbow method. So we will use sklearn.cluster module and import k-means class. After that, we will take an empty list, which is WCSS, and then we will use a for loop in the range of 1 to 10, which depicts the number of cluster in the range of 1 to 10. In this for loop, we will initialize our class k-means with the object k-means, and we will pass 3 parameters. The first one is the n clusters, which depicts the number of clusters, and it is equal to I. Then the initialization method, which is we use k-means plus plus to avoid random initialization trap, and the third parameter is random state, which is equal to 42. After this, we will fit our k-means algorithm. So k-means dot fit, and we will pass feature of matrix X. After this, we have to calculate the summation of distances of points and centroids in the cluster, and for this we will use k-means dot inertia, and so we will append the k-means dot inertia values in the WCSS matrix. So this code in the for loop is completed, and after this we will plot this result in graph to see the number of clusters. So for this we will use range 1 to 10 as our x-axis and WCSS value as our y-axis. And the title of the plot is the elbow method. The x label is the number of clusters and the y label is WCSS. So let me first run this code and show you that how the elbow method plot looks like. So this is how it looks like. As you can see, when the cluster value is equal to 1, the value is much more high, and when it changes to 2, the value decreases drastically. When the number of cluster changes to 3, it again decreases. When it changes to 4, it again decreases, and when it reaches 5, the number of cluster equal to 5, after that, if you change the number of cluster, the decrease is not as sudden in the previous cases. So we can now choose that our optimal number of cluster is equal to 5. So now we will rewrite this k initialization code, and instead of the n clusters equal to I, we will now write n cluster equal to 5. Now the rest of the code is same, and instead of using the fit method, we will now use fit predict method to predict our clusters. So let me first run this code, and we can see now our y means variable is consist of now the number of clusters which each customer belongs to, and their ranges from 0 to 4. Now after that, now we have to visualize what we have predicted in this model. So for this, we are using plt.scatter, and in this our x-axis is y means equal 0, which means first cluster, and comma 0, which means the first column of x-axis. After that, and similarly now x in square brackets y means equal 0 first cluster, comma 1 which means second column of feature of matrix X. Then S equal to the size of dots which we are plotting, so equal to 100. C is equal to color which is red, and label equal to cluster 1. Similarly, we will repeat this step for all the clusters. After that, we will also plot the centroids of the clusters. For this, we are using k-means dot cluster underscore centers underscore, and now we are passing all the clusters, that's why we are using colon comma 0 which is the first column of feature of matrix X. Similarly, in this y-axis we are passing all the clusters and second column of feature of matrix X. Now here the size of centroid is larger than the points of the cluster, that's why it is 300. The color is yellow and the label is centroid. Then the title of the plot is cluster of customers, and X label is annual income, Y label is spending score. So now we can plot this graph. So let me run this code and we can see our plotted graph. So this is the plotting of our graph. Now you can see that our cluster 1 is of red color and they are in the range of average annual income with average spending score. Now the second cluster, which is blue, having high annual income but their spending score is less. And our cluster 3, which is green color, has low annual income and low spending score. Now our cluster 4, which is of cyan color, has low annual income but they spend higher because their spending score is higher. Now our cluster 5, which is of pink color, has high annual income and their spending score is also high, and these yellow dots are the centroids of our cluster. So this is all about k-means algorithm. Thank you for listening this session.
Hello friends, welcome to the course on machine learning. Today we are going to talk about hierarchical clustering. Now, hierarchical clustering is a part of algorithmic clustering. There are basically two types of clustering, algorithmic and decisive. Algorithmic clustering uses a bottom-up approach, whereas decisive uses a top-down approach. We are going to talk about hierarchical clustering, which uses algorithmic approach, like that is bottom-up approach. So how it works? Let's see. First, let's try to understand it with an example. So consider there are 6 data points, as you can see here in the image. These 6 data points are available. Now what's going to do is it's going to go with the bottom step, that is treating all the data points as a separate cluster. So the first step of our hierarchical clustering will be treating or making all the data points as a separate cluster. So as you can see, there are now 6 clusters available because there are 6 data points available in our data set in this example. So now the next step is it will calculate the distance between all the data points from each other, and it will use those 2 data points which have the minimum distance between them. Now the distance can be calculated using various metrics such as Euclidean distance or Manhattan distance or anything. So here, as you can see, these 2 data points having the minimum distance between them, so it's going to create a clustering and it will be treated as a one cluster. And the same process goes on until we get a single cluster out of all the data sets. So first it will create a cluster of these 2 data points. So as you can see in the next image, it created a data cluster of these 2 data points, and now we have 5 data clusters available. Now it's going to repeat the same process. It's going to calculate the distance between all the data points and create a new cluster out of the 2 clusters which have the minimum distance. So here in this data points, these 2 data points have the minimum distance between them, so they are going to be created as a single cluster. So as you can see, it created another cluster, and now there are total 4 clusters available. Now the same process goes on until we get a single cluster. As you can see, it's created another cluster, and then it will create a cluster of these 3 data points, that is this cluster and this cluster. So it will create another cluster, and now by default there are only 2 data clusters available, and this will be 2 data clusters with the minimum distance available. So it's going to create a one large cluster out of these 2. So as you can see, and now it will finish the process. Now this is the basic process of how hierarchical cluster works with the data points. But hierarchical cluster, in the process of hierarchical clustering, it stores all the steps into the memory, and the memory representation of the storage is referred as dendrogram. Now we will talk about the dendrogram later. First we will talk about how it calculates distance between the data points or clusters. So there are basically 4 approaches then, or 4 options available to calculate the distance between the data clusters. That is, first is closest point. It's going to calculate the distance between the 2 closest points of the cluster. So it's going to calculate the distance between these 2 clusters by calculating the distance between these 2 closest points. Similarly, the second approach is furthest point. That means for this cluster, this is the data point, and for this cluster it is the data point. So it's going to calculate the distance between these 2 data points to calculate the distance between the clusters. Now the third is the average distance, in which it calculates all distance between all the data points from each other, and then converting into an average value. And similarly, the fourth option is calculating the distance between centroids. I mean, it will calculate the centroid of the cluster first, and then it will calculate the distance between those centroids. Now these are the 4 approaches that our hierarchical clustering uses. We are basically going to use the distance between centroid approach. So let's see how dendrogram works, how it stores all the steps from initial to the end when we get a whole huge single cluster. So let's say we have an example where there are 6 data points available from P1 to P6 in this graph, and let's say this, now the second graph is our dendrogram graph, in which the x-axis is the data points that we have from P1 to P6, and y-axis is the equivalent distance between these 2 data points. So first, our hierarchical clustering is going to treat all the data points as a separate cluster, and then it's going to calculate the distance between them. Let's say we are using an equivalent distance between the clusters. So let's say in this example you can see that the P2 and P3 data points having the minimum distance, so they are going to be converted into a single cluster in the next step. So when it converts them into a cluster, it's going to calculate the distance between them, which will be the equivalent distance between these 2 clusters, and then it's going, in the dendrogram, it's going to plot a horizontal line first of that specific distance between these 2 clusters. Let's say it's about 0.5, so it's going to create a horizontal line at 0.5, and then it's going to join both these data points with the horizontal line vertically. As you can see, P2 created this vertical line and P3 created this vertical line, and now in the dendrogram this is representing a cluster. Now why we use distance between the data points? Now you may think of it, so distance is kind of showing a similarity between the data points. As you can see, let's say for the P3, P2 having the minimum distance, that means it will show much more similarity with P3 compared to the P4, P1, P5, P6, I mean all the other points, because it's having the minimum distance between them, so it's going to show a more similarity compared to all this data points. So we are going to use distance. So in the next step, it's going to find out the minimum distance between the other clusters, such as in this example P5 and P6 are having the minimum distance between them. So it's going to create a new cluster out of it, and then it's going to create a horizontal line of that specific equivalent distance in here, and going to create vertical line from 0.5 and 0.6 to join it, and then it will be treated as cluster. And then it will create and calculate the distance between them, and going to plot a horizontal line at the specific distance, and then it's going to create vertical line from those points to join this horizontal line. As you can see, 0.5 to here and 0.6 to here. Now the same process is going to repeat one after another. So in here P1 and the cluster of P2 and P3 will have the minimum distance, so it is going to plot a horizontal line in dendrogram with that specific distance, and then going to create a vertical line from the clusters. So in the next step, as you can see, it will form a new cluster here because they are having the minimum distance in between all of them. So it's going to plot a horizontal line at the specific distance and then going to create vertical line from the data points. So here it will be P1, and for second that is cluster of P2 and P3, so it will create a vertical line from here. Now similarly P4, and this cluster is now having the minimum distance between them compared to all, so it's going to create a cluster here, and then it's going to use the equivalence distance between them to create a horizontal line and then create vertical line from those data points until it connect with the horizontal line. So as you can see here, it created a horizontal line here and then created a vertical line from here and the cluster here until it connects the horizontal line. Now similarly, now by default these two clusters are the only remaining clusters here, and then it's going to calculate the distance between them, and by default it's the minimum distance available right now. So it's going to calculate distance between them, plot a horizontal line in the dendrogram, and then will merge both the clusters, and so it will form a new cluster. Here as you can see, it created a horizontal line of that Euclidean distance, and then it created a vertical line to join the horizontal line from this cluster and the second cluster. Now the whole process was about to converting them into a single cluster. But how we are going to find out that what is the optimal cluster, or how many clusters we are going to get? So for that we need to set a threshold value for of Euclidean distance. Now the threshold value, for that specific threshold value, it's going to create a horizontal line, and then number of vertical lines that intersect the threshold value will be the number of clusters it's going to create. Let's say we set 1.75 Euclidean distance as a threshold. So the horizontal line here is intersecting two vertical lines. So it's going to create two clusters out of it, and those clusters will be, the first cluster is this P1, P2, P3, and second cluster will be this P4, P5, P6. So as you can see here, we created two clusters. Now let's say the threshold value will be around like 0.75. so the horizontal line will going to intersect with the four vertical lines, as you can see here, 1, 2, 3, 4. The model is going to create four clusters, so which will be the first P1, and then second is the cluster of P2 and P3, third is P4, and fourth is cluster of P5 and P6. So P1, cluster of P2, P3, cluster P4, cluster P5 and P6. Now even if we set a threshold value of around like 0.25, so it's going to intersect 6 vertical lines, so it will split in them into 6 clusters. Now that's how all it works. Now here our model of hierarchical clustering is about to setting a threshold value which will split them into different number of clusters as required. But the optimal approach is to find out the largest vertical line first in the dendrogram and then splitting it with a horizontal line, and then the number of vertical line it intersect will be the number of optimal clusters that can be obtained from our model. That's all the intuition behind our hierarchical clustering. So let's try to implement into our code. So first we are going to import all the important required libraries such as NumPy, Matplotlib, and Pandas. Now after that we are going to import our dataset. So here first let's create a data frame named dataset using Panda library and using its function read CSV, in which we are going to pass a CSV file which is mall_customers.csv. Now this is the dataset that we are going to use, and what kind of problem we are going to solve is that let's say we have information regarding mall where we have data of users, or I mean the customers, that having their gender, their age, their annual income in thousands, and their spending score from 1 to 100. And spending score depends on how much amount they spend in the mall and how regular customer they are and things like that. So let's say we are going to create a hierarchical clustering model which is going to split these customers into separate categories. Let's say it will divide them into clusters, such as a cluster of customers with high income and high spending score, or the customer with low income and low spending score, and some customers which are having low income but still they are having high spending score because they are spending much in the mall, or they may be a regular customer or things like that. So in this way they will cluster the customer into different categories, and then they are going to treat them accordingly. So in order to do this, we are going to require two columns from our data set, which will be their income and their spending score. So in order to create a training data set, that is X, we are going to use these two columns. So let's say X equals to data frame, which is our data set, and we are going to use .ilog method, in which we are going to pass column for all the rows, and then we are going to pass a list of value 3, 4, which will denote our column third and fourth. I am going to use dot value so that it will be treated as an error. So after executing these two lines of code, as you can see, then we created data frame named data set of whole data set, and then we created our training set, which is our annual income and their spending score. Now after that, before implementing our hierarchical clustering model, we need to first implement our dendrogram, so that we can see how many number of clusters possible, or how many optimal number of clusters can be created. So in order to create a dendrogram, we already have a library available in SciPy, that is scipy.cluster.hierarchy. In this package there is already a class available that is referred as dendrogram. So we are going to create a dendrogram from it. So let's import the library first. So let's import the package first, that is import scipy.cluster.hierarchy, and then let's say assigning an alias as sch. So we can use sch instead of the whole package name. So we are going to create a variable of dendrogram using dendrogram equals to sch.dendrogram, where in which we are going to pass first our linkage sch.linkage, where we are going to pass our training data set first, that is our X, and then method is equals to word. Here method is equals to word refers to the word as centroids. Now as you remember, there were 4 approaches available to calculate the distance between two clusters, and out of those 4, word referred to the distance between the centroids of the two clusters. So that's how we are going to use method is equals to word. Now and then we are going to create plot with the title dendrogram. We are going to label it as a X label as a customer and Y label as a Euclidean distance, and then we are going to show our plot. So after executing this line of code, as you can see, we got our plot of dendrogram, which is this. As you can see, it created the dendrogram of all 200 data points from start to end until it converted into a whole big one cluster. So it is referred as bottom up approach, where it starts with all data points as separate cluster to a whole big cluster. And now using the optimal approach, that is by splitting the largest vertical line from the center. And as you can see, so the largest vertical line is this, and using the center and splitting it from the center, as you can see, it's going to split them from here, and the vertical line it will intersect will be 1, 2, 3, 4 and 5. So there will be around like 5 clusters that can be formed. So we are going to use number of clusters as 5 for our hierarchical clustering. So after seeing the dendrogram, we are going to implement our hierarchical clustering model. So for that, we already have a algorithmic clustering class available in cluster package of scikit-learn. So we are going to import it first. So from sklearn.cluster, we are going to import algorithmic clustering. After importing our required class, we are going to create a first variable or object of that class. Let's say which is hc, which is referred as hierarchical clustering. Hc is equal to, then we are going to use the constructor of a class, that is algorithmic clustering, and then we are going to pass required arguments, and these are first n clusters, which is the number of clusters. The optimal and best possible number of clusters is 5, so we are going to pass n underscore cluster is equal to 5, and then we are going to pass affinity, that is the method that we are going to use for the calculating the distance between the clustering. So let's say we are going to use Euclidean. You can also use Manhattan here, or L1, L2, and there are different approaches. You can see the scikit-learn documentation. Now here we are going to pass affinity is equal to Euclidean, and then we are going to pass linkage equal to word, so that it will calculate the distance between the two clusters by calculating the distance between their centroids. So after executing this line of code, we created an object of our hierarchical clustering. Now we are going to fit our model, and then we are going to make prediction of it. So first we are going to use hc.fit_predict method, and then we are going to pass a training data set, that is x, and then the prediction that is going to make on those data points will be stored at the new variable, that is y_hc. So after executing this line of code, we will get an y_hc as a new variable. As you can see, it's assigned its cluster number to all the data points of the training set, that is x. So as you can see, for the data point where the customer with this annual income of around like 15,000, but its pending store is around 39, so it represented to a cluster number 4. And similarly for the second user is a part of cluster number 3, and third data point, or I mean the third customer, is a part of cluster number 4, and things like that. And in this way we splitted the malls customer into separate categories using the hierarchical clustering method of machine learning. Now that's it for our today's session.